member for us. And from the discussion we have, we are very happy that participants were very active through the question and uh, through the chat room and even from the YouTube channel that we have. So we do hope from this day three we will have a same happiness to join to discuss and to contribute to this very important session and topic for us. Thank you, Sheila.
Thank you, Buneli, for your wonderful yesterday evaluation. And then I hope all the participants still have the same spirit as yesterday. And do we have Sydney now? Sydney, can you hear me?
Yes, yes.
Okay, thanks God that's you.
Sheila. Yes.
Maybe you could deliver some refreshment from yesterday's meeting, please.
Oh, terima kasih. Thank you, Bu Sheila. Yes, we had an excellent climate science breakout group led by Professor Carl Schreck from the North Carolina Institute of Climate Sciences, where Carl introduced the type of equatorial waves, Kelvin waves, Rossby waves, gravity waves, and MJO, and how to monitor those waves. And that was a very important topic. Indonesia is among the top 6 countries using those data. And then in the ocean science breakout room, we heard 4 outstanding presentations. The first one was from Dr. Chidong Zhang at NOAA's Pacific Marine Environmental Laboratory, where he talked about the years of the maritime continent. And Professor Arnold Gordon delivered an excellent talk. Arnold is from Columbia University, where he talked about the Indonesian through-flow Minty project. Janet Sprinthal is from Scripps, and she talked about the equatorial line observations. And then we concluded with a general lecture, actually in Jakarta, by Halda Adita Belgama, where she talked about the weather research forecasting model. And we have a similarly exciting agenda tonight. If you'd like me to take just maybe 1 minute to just go over what we'll be doing today, if that's okay.
Yeah.
Terima kasih, Bu. In the climate science group, we have Dr. Dick Arndt from NOAA's National Centers for Environmental Information talking about methods in extreme climate analysis. And we have our dear colleague, Marina Timofeyeva, who's been with us for many workshops in Indonesia, and she'll be talking about applying climate information for decision support services. And then we have Kathy Smith from NOAA's Boulder, Colorado laboratory doing NOAA climate analysis and plotting tools. And we have 4 outstanding presentations in the ocean group today. Professor Scott Glenn from Rutgers University near New York City. He'll be talking about sea gliders. Professor Stephen Reiser from University of Washington will be talking about Argo profiling float technology. Luca Sentironi is from Scripps Institution of Oceanography talking about drifting buoys. And NOAA is developing a new directional wave spectral drifter. And we shipped 2 of those to Jakarta just several months ago. And then we'll conclude the ocean science session with Professor Eric Terrell from Scripps. And he'll be talking about quality control methods for HF radar. And then at the end of the 2 breakout groups, we'd request kindly that everybody reconvene in plenary. Bu Nelly and I would like to make a few brief concluding remarks to wrap up this amazing 15th annual NOAA Indonesia workshop. Terima kasih, Bu.
Okay, thank you, Sydney, and thank you for your informative information. And then we will keep in mind that we will have the closing with Pak Sydney and Bu Nelly as well. So do we have Pak Dodo here? Maybe Pak Dodo could give some additional comment if he wants. Pak Dodo?
Okay, thank you, Sheila. Good morning, Indonesia College, and good evening for the US College. Yeah, uh, thank you, Pak Sydney, for your review for yesterday. Our two classes we have yesterday. Yeah, I was in the climate room. It is very interesting topic that we heard all from Dr. Chris. It's we really uh, need such such a tool that introduced by him. Then maybe it is should use it for uh, our analysis and for prediction as well. Yeah, actually, I was thinking that it is actually really hard to split this materials, this topic on the ocean and climate, as the ocean also for our climate communities, of course, is very important. That actually ocean is the memory for climate as well as the land. So I was thinking that maybe in the future we should also how these all important materials topics could be we could have all of this for climate for climate purpose as well as for weather in ocean in the lands as well as interaction with atmosphere. So yeah, next maybe we should think about this. This is because of the restrictions of the time when we would have the series for this talk. Of course, it's time is very limited, so we will think next with Pak Sydney how this all actually topic we will have to get it. For today, I would like to thank to the lecturer, to the research person from US for NOAA, and also we have still have some Indonesian maybe get the presentation. That's it. I think my comments, and welcome back to all participants, and have a nice class for this nice discussion. Thank you, Sheila.
Okay. Thank you, Pak Dodo, for your additional comments. So this is just a short announcement. As of yesterday, 2 parallel classes will be open. For lecturers and participants under this ocean topic, just please stay in this room. Mr. Iris Ardianto will be act as a moderator. And for those who are in the climate topics, please migrate to another link. The link will be shared again in the chat room box in case you forget. In the climate class, Mr. Siswanto will be act as the moderator. I would also like again to remind all the participants of the climate class to be back online in this link, in this plenary link, once your meeting in the climate class is finished. Then we will have the plenary closing and then the general lecture. So I guess that's all from me. And dear participant, we will have a 10 minutes break for the parallel class preparation. So I hope you have a fruitful discussion, and I'll see you soon. Thank you.
Thank you Mbak Sila.
Dalam bahasa Indonesia juga mungkin pengumumannya.
So,
Oke. Selamat pagi kepada Bapak Ibu para peserta 15 Annual US NOAA and BMKG Partnership Workshop. Jadi sama seperti dengan hari kemarin bahwa pada hari ini kita membagi 2 paralel kelas, yaitu kelas Ocean dan kelas Climate. Untuk kelas Ocean bisa stay di link ini sebagai plenary room, dan untuk kelas Climate bisa migrate ke another link atau pindah ke link yang lain, link Zoom yang lain yang akan disediakan oleh panitia di chat room box ini. Apabila ada pertanyaan, bisa ketik di chat room ini atau menghubungi narahubung. Nanti setelah selesai meeting di sesi Climate Topics, mohon untuk kembali online di link plenary room ini untuk kemudian kita mengikuti sesi wrap up dari Bapak Sydney dan juga Bu Nelly. Kemudian setelah itu kita akan memiliki general lectures dan akhirnya diakhiri oleh official closing oleh Bapak Dr. Dodo Gunawan. Demikian. Terima kasih.
Arif.
Yes.
Nanti kalau yang pengajar klimat masih ada yang tertinggal di sini diinfokan ya, saya live. Oke.
Mbak Sela kalau mau join kelas klimat silahkan.
Oke.
Hi, Luca, or maybe Sydney. I cannot see Eric. Is he here or late already? Eric Terrell.
I will look in the participants list, Pa. I didn't see him. I looked. Yeah.
Yes, that's why maybe he
But
haven't joined us.
Yeah, he's last presenter, so he may come in a little bit later.
Yes.
Yeah, I don't see him, Pa. I see Luca. Yeah.
Yes. Hi, Luca. Good evening. Sorry.
Yeah, I don't see Eric Terrell, but he will be here for his presentation. Yeah.
Hi, Luca. You can unmute now. Sorry.
Thank you. Good morning, everyone. No, unfortunately, I don't know about Eric.
Hi, Luca. How are you?
Good. I'm in Italy.
Oh, you're in Italy. Wow.
Yes.
Oh. So it is late, very late at night, I think.
Yeah, or very early in the morning, depending.
Yeah, already in the morning. Sorry.
Oh my God.
3 in the morning.
Yeah.
So I ask you for your forgiveness if I misspeak.
No, it's fine.
Yeah.
Thanks for joining, Luca. This is great.
Yeah, thank you for
It's my
joining.
pleasure. Thank you for inviting me. That's very great. Thank you.
And hi, Steve. Good morning. Good evening. There.
Good morning, everyone. Good morning.
Yes.
Good morning.
Professor Riser.
Nice to see you all again.
Yes, nice to
See
see
you,
you.
sir.
Very interesting meeting.
Yes.
Pengumuman Bapak Ibu-Ibu, di sini adalah kelas Ocean. Bagi yang ingin mengikuti kelas Klimat, silahkan follow link berikut. Pak Riris, mungkin bisa dimulai.
Oke, Mas Arif. Ya.
Good morning, everyone, and good evening for our colleagues in US and other parts of the world, especially Luca in Italy. So let's begin our session in this morning. And this is a breakout session for Ocean Science Group. And I'd like to convey sincere thanks for all of the panelists, invited panelists, and also all participants for joining in this event of 15th Annual Indonesia-US Partnership Workshop. And thank you for being here today. This morning, we will have 4 presentations in this session, and each presentation will be 15 minutes, followed by a question and answer session for another 15 minutes for each panelist. And then after 2 presentation and QA, we will have a short break for 5 minutes. And then after that, we continue with the rest of 2 panelists. So let me shortly introduce our distinguished presenters or panelists that joining in our session. For the first presenter will be Professor Scott Glenn. He is a distinguished professor from Rutgers University, and he already involved in development of new autonomous ocean observing technologies, their application for scientific research in remote and extreme environment. And then his major scientific focus is in extreme weather events, including storms, hurricanes, typhoon, etc. And I think Professor Scott Glenn are very familiar with Indonesia. So we hope that you can share your expertise to us here regarding the latest technology and especially in ocean instrumentations. And then the second panelist will be Professor Stephen Reiser. He is a professor in oceanography from University of Washington with long-term interest in the interaction of physical and chemical aspects of the circulation of large-scale ocean. He focused on profiling float technology that widely spread all over the ocean world. With his laboratory, he has pioneered the use of many technologies, presently using modern profiling floats, include the additional biogeochemical sensors, and etc. So it is really lucky for us to have both of you here to share your knowledge in this first session. So without delaying time, I would like to invite Professor Scott Glenn for presenting his lecture for this morning. Professor Glenn, the floor is yours.
Thank you. And thank you for inviting me to this again. I'm very honored to be here. Am I going to share my screen, or are you going to present my talk?
Yes, you can share your screen.
I will try that then. All right. I'm not sure if you're seeing that.
Yes,
we see it.
And now I put it in the play mode. You can probably even see my arrow. Is that correct?
Yes, we can see it.
Fantastic. Okay, so Sid asked me to speak on ocean gliders to help researchers solve key climate questions in Indonesia. And I thought that was a really exciting topic. Thank you, Sid. I don't solve many key climate questions myself in Indonesia. So I had to come up with another place that I could show some demonstration of the technologies. And I thought that the Caribbean corridor would be a very important place for that. And that's because in that corridor that goes through the Caribbean from the open ocean there, I can point from the open ocean here, the circulation that goes through the Caribbean into the Gulf of Mexico and out again. That has an important piece. That's an important piece of the global circulation. And it also has a big impact on hurricane forecasting, which has drawn me in. And because hurricanes happen year after year after year, we're there year after year after year. And pretty soon that adds up to climate scale activity. And so that's the area that we're going to work with. Many partners that are involved directly in this piece of it, they're listed there. So, oh, I got to move this here. Okay. Here's the diagram that shows how we're related in this area. I've got the two circles, two yellow circles around these two areas. And you see the global conveyor belt here, the thermal haline circulation. You can get many photos of that online, many images, and they're all slightly different, but they have some of the same key features. And one of the key features that we're emphasizing today is this warm, shallow current, the warm, shallow current that goes through Indonesia, the Indonesian through flow, and then again, the piece of that same warm, shallow current that you see going through the Caribbean. And there's some features of this current and also of the topography in these areas that is similar. In particular, there's a lot of islands. And how do we take advantage of those islands to help us sample in this area? So let's zoom into first the Indonesian side of it, and then we'll zoom into the to the side in the Caribbean by the US. I have to get this other. There. Have to move all of our photos out of the way to get to the arrows. Okay, here's a paper by one of the people that I've worked with, Tony Song, in the past, off of New Jersey, where they used a lot of satellite and gravity data to look at the flows in this region, the Indonesian flow through. And what I like about this is it talks a little bit about the processes that are going on, and that there's that Indonesian flow through in red, coming through here is what they call these things, the South China Sea through flow in green, and here the Maluku Sea through flow coming in. They all mix together in the Banda Sea. That's where the mixing, and then they all flow out down here by Timor and the Mumbai Strait. And so that's, you can see many diagrams of this. And sampling, there's a lot of shipboard sampling, moorings, something that might be in different places. But what I like is the very first couple of sentences of their abstract, which is up here. Says how the Indonesian through flow plays an important role in global ocean circulation and climate. So, okay, it's very important. The next sentence is, yet measurement is difficult and expensive. And so that's the part that, I kind of key in. It's very expensive to measure these types of systems. And how can we do that? How can we take advantage of the passages and the land masses that we have, all the different islands in this area, to help us with that sampling? Okay, my next slide. So now we move over to the Caribbean, to this area here of the Caribbean that we are talking about. And these were some of the papers that motivated us back in early 2018, where they were looking at, in Nature, they're looking at how the circulation in this area looks like it was slowing down. And they had evidence of that and how this was changing, because this Atlantic meridional overturning circulation in this area it's the thing that we see in the rapid climate change scenarios. It's changes in this that can cause some of that rapid climate change. So monitoring this is very important. And they even put in a editorial about how this ocean circulation is changing, and we need to know why. And it's essential down there. It's essential for to monitor this and work out how it alters the climate, because it's going to affect the whole planet. So, okay, that was a lot of motivation for us to see how this warm water was coming up through the Caribbean and the Gulf of Mexico, and then up the East Coast, and then heading off towards Europe. We also had another reason for going into the Caribbean to look at this, and that's shown in the next slide. Oh, here's that expensive way of monitoring. The moorings that they would put in. Up along the north, there's the OSNAP array that it goes in this part of the northern part of that circulation, in the areas where there's a lot of that deep water formation, and then the rapid array that goes across the Atlantic here. And you see the arrays on the right, there's a lot of moorings that are involved, very intense moorings, a lot of shipboard work, just like they said in that other paper, very expensive. And so we were looking for the ways to help monitor this current in areas where we could do it less expensively and still get important information to inform this community. And that's our area there that we care about. We want to look at it through the Caribbean, where instead of having to go out there with moorings or go out there with boat platforms, we could use the islands as platforms. Here's the other motivation that we have. Here's that warm water that goes through the Caribbean, this pool of warm water. This is the ocean heat content contoured in the colors here as you go along this route. Along that same route is the route that the hurricanes take. And the dots in this are areas of rapid intensification. And we're not very good at forecasting when a storm rapidly intensifies or when it rapidly weakens for that. Rapid intensity changes are very difficult for us to forecast. And here's one of those motivations right there. 39 cases of rapid intensification were observed in 2017. 2017 is the year that we use as our baseline. Only 6 were forecast. And so we want to start doing better than 6 a year and be able to, our ability to forecast these. And most of the big ones, most of the big rapid intensification events occur right along this track that warm water flow is going through the Caribbean. And so if we can go in there and monitor this for hurricanes, and we have to do this year after year, we can then contribute to the climate impacts. And so that's our study region for this. And the hurricane work is really motivated by all the damage that they can cause. And so here's the NOAA tabulation of all the weather and climate disasters and their impacts on people in the US for the last 40 years, going back to 1980. And if you rank them by cost, how much damage they did, or by deaths, if you look at the deaths, 6,500 deaths due to tropical cyclones, these hurricanes, they cause more deaths than any other category of climate or weather disasters in the US. If you look at the costs, they cause more damage than all the other weather and climate disasters combined. So this is a very important piece. All these things are affected by climate. Some of these are weather impacts that are affected by climate. They're all important, but tropical cyclones are very important. And so we have a lot of reason to be out there sampling the tropical cyclones and improving those forecasts. And here's the critical piece that definitely needs improvement. If we look at on the left-hand side is the improvement in track over the last 30 years, since 1990 there. And if you look at those are the forecast error trends. How are we doing with forecast errors? 200 to 400% improvement in track. So we've been doing a great job of improving the track forecasts. But then if you look on the right, those are the intensity forecasts, and the improvement there is lagging. It hasn't been as great, 20 to 30% over all those years. And the hurricane decisions, whether you evacuate or shelter in place, they're made several days in advance, and they're based on where it's going to be, where the hurricane's going to make landfall, which we're pretty good at predicting, but also the intensity, which we're not very good at predicting. And the intensity is critical because if it's not an intense storm, you'll typically shelter in place. But it's a very intense storm, you have to evacuate. And you have to have that warning like at least 3 days in advance so that you know, so that you have time to leave and pack up all your things and get everybody out on the roads that can only handle so many people. So if we look at the intensity, there's a few things that usually balance the intensity of a hurricane as it's coming ashore. Those things, one is like the ocean temperature, the sea surface temperature, and the ocean heat content. How much heat is in the ocean, because that's the energy to intensify it. And there's also wind shear at the top. So if there's a lot of high wind shear, that pulls the top off the hurricane. So it's this battle between the atmospheric interactions at the top of the hurricane, the wind shear trying to squash the hurricane, and the energy source at the bottom. If the ocean is warm, it's going to intensify the storm. If the ocean is cold, it's going to weaken the storm. And seeing that we were so bad at intensity there, that wind shear up at the top, that's what the global models get us. We get that from the global models that are out there. But the ocean, we have to get that from the ocean models. And if the ocean isn't, if the ocean models aren't good, part of it could be because they don't have the data to assimilate. And so how do we get that assimilation data? And that's one of the things that we are putting together, both for hurricanes and for climate. And so the gliders are one of our key technologies for this. They're, here's a brief history over the last 20 years. 1999, put the first Slocum gliders in the water off New Jersey. About 10 years after that, we were able to cross the Atlantic. And 10 years after that, they're a key part of the strategy now for the NOAA's unmanned system strategy, and specifically being used a lot for hurricanes. So 20 years of experience doing this, building it up year after year after year to this point now where they're pretty well understood and now being applied to issues that NOAA cares about. For some in the audience that don't know what a glider is or how they operate, here's the Glider 101 book on that. The underwater gliders, they don't usually have propellers. They can if we want to put some of them on them for emergencies or whatever, but they mostly work with a buoyancy pump propulsion, where the buoyancy pump, it'll pull water in, changes the volume, and the glider sinks, and the wings have it fly forward. Then it gets down to the bottom, the water's pushed out, changes the volume again. The glider starts to float up to the surface, but because it has wings, it flies forward. So it flies down and up, unlike a glider in the air where it just flies down. These fly both directions, up and down, through the water column. And they really don't use much power, very low power. And as a result, that allows for a very long duration, typically on the order of a month or a year. They have a very flexible payload bay, which is one of the keys to the mission. So it's like, the space shuttle. If it fits inside, it can fly. And as a result, you can put in many mission matched sensors into the gliders to for whatever your mission is. And that's one of the big growth areas right now is what different sensors can you miniaturize and make low enough power to fly on these platforms that are pretty well proven now. They surface at regular intervals for satellite communications. They check their GPS location. They transmit their underwater data to the glider operations centers, where it gets moved over on the GPS so it can get to the operational modeling places, and it checks to download any new commands for its next mission. So they're very flexible. You can move them around as you need them. So that's a quick primer on the gliders. One of the nice things about gliders is they fill a sampling gap between what Argo floats typically do and what dedicated ships typically do. These are the places that you usually go to get a profile. If you need profiles, you might hire a ship, and you'll be charged in ship days. You get 5 ship days, 10 ship days, something like that. So the time is measured in days. Argo floats are at the other side, where they're very, very low power, and they can last for years. And so it's like, how many years can you get out of your Argo floats? And gliders are somewhere in the middle. You have a little more control, but you have to pay with less, with more power draw. And as a result, your duration is now months. And so as you go across there, there's increasing human capacity. There's more control, but there's cost and human involvement go up. And those ships, very expensive to operate. People have to be on them. And in this time of COVID, the autonomous systems that are over more on the left grew to be very popular, because they could be deployed with a small number of people and still get many of the samples that we needed. And so these are all very complementary. You'll always have ships, you'll always have Argo floats, and hopefully you'll always have underwater gliders in the middle, filling the sampling gaps between them to get the profiles, get the vertical profiles. In this region, we then defined the regionally specific essential ocean features that impact the hurricane intensity. And there are different features in different regions. And so ocean heat content is kind of important for all these things, right? But there's different things that impact that ocean heat content. The Gulf Stream can impact it. There's a lot of heat in the Gulf Stream in the loop current. But there's also other pieces in this, like in the mid-Atlantic where I live, we have the cold pool. There's a bottom cold pool of water that's down there that can get mixed up in a hurricane, rapidly cool the surface and weaken the storm. And the other piece of this is the fresh water. There's fresh water from the rivers, the Amazon and the Orinoco in the South America, that flow into this region and make a surface layer that is very fresh and can inhibit mixing. And if you inhibit mixing, you can warm the surface much fast. The first surface stays warm and you can intensify the storm. We also formed teams over all these regions, so we could establish the teams to do this and demonstrate that distributed autonomy that we care a lot about. So it's not one place that has everything in case that place gets hit by a hurricane or gets hit by COVID. It's distributed. So if some place goes down, you don't lose the entire network. And here's our ConOps, our concept of operations. The hurricane hunters, they've been doing their job for a long time, since 1946. And it's like a soccer game. They dress in white and they fly through the air and they chase the ball. So they're chasing the hurricanes. The gliders, on the other hand, just like the goalie, they dress in yellow and they protect the goal. And so the gliders are all in place before the hurricane gets there, getting the ocean models on track before the hurricane hits. And here's one example of that from 2018, one of the first sets of hurricanes that happened with the glider fleets deployed. And there's the distributed fleet, the picket line up around the US East Coast, another one in the Caribbean, around the US waters there, Puerto Rico and the Virgin Islands, and then one in the deep ocean as the hurricanes were coming along. And it's all a large group of people all working together. Here's a summary for 2019. In the bottom, you'll see there's the full tracks of the hurricanes, which are in gray. They go all over the ocean. And then the red tracks are the last 3 days before landfall. And that's the time when you have to make that evacuate or shelter in place decision. And then up in the top diagram, you see how the different sampling technologies contribute to this. The Argo floats, they're all over the ocean. They're everywhere. And they stay out for a long time. They're distributed. And so those Argo floats coming up once every 10 days, they're getting the gray part of the tracks. As they're way off in the deep ocean, as they're coming in, getting that ocean correct there. And then as the hurricanes are approaching land, where you need more and more data and you need more and more resolution from the data and things are going to happen fast, that's where the gliders come in. And those are the red tracks. And the red tracks are all in the shallow waters, in the coastal waters, or right in the islands as they're approaching. And that's one of the important pieces that we have for these gliders to do, one of their jobs. So now let's look at the Caribbean. And in the bottom row is the surface salinity from one of the models. This is one of the critical parameters that's coming in. The Amazon is over on the right. It's bringing fresh water into the Caribbean. It all goes through the passages. Remember that warm layer of ocean water that was going through the Caribbean, and it's coming in there as part of the global circulation. It's bringing that fresh water in, and it's circulating around the Caribbean based on the mesoscale that's out there. And so it looks pretty good. And compared to what the ocean color imagery is above and the top, it has the same scale of features. But is the magnitude correct? We can't tell that from the satellite. We see the same features, but does it have the salinity? Because that absolute salinity matters, whether it's going to mix or not. And so to do that, we want to look at the flow of salinity or heat or mass that's coming in through the passages. And those are those through flows. How do we get those? And so here's one of the examples what we did in 2018, where we put 3 gliders in a triangle in the Anegada Passage. The Anegada Passage is one of the deep passages between the islands. And so we chose a deep one. It's also in US waters, so it was very easy for us to look at. And we looked at the glider, which is in blue, the currents, the depth average currents, compared to the model, which is in red, the global ocean forecast model, the Navy model, which was a very good data simulative model. And we found that the flow through the passages was in opposite directions. Here's one of our best models, one of the best global models, data simulative, and it has the flow going the wrong way in the passage. And that's not going to help us get the right magnitude of those barrier layers. And so we did, here's just the mean of that. You can see the red arrow for the model is going out. It's transporting heat and fresh water out. And the gliders are showing that the transport is going in. And so because we had a triangle of gliders there, we could look at the temperature and salinity at each of these and calculate the density. And with the density between the top and the bottom, the blue and the green up here, this top and this bottom one, you can do the thermal wind calculation. And you can apply that thermal wind calculation of the current to get what the shear is at the orange one in the triangle, in the middle of it. And so that's why we put a triangle out there and kept it out there for a long time in the passage to monitor the flow. And then here's the result of that. On the left-hand side, you see that there's the blue line is the thermal wind between the 2 gliders at the blue and the green at the top. The offset between the depth average current and the current at the orange glider is shown here in the middle. You adjust that. You then get the absolute current. With the absolute current, you can multiply it, current profile, you can multiply it by the temperature profile, and you get this, where the model still has heat, in this case, transporting out of the basin and the glider's saying it's going the other way.
Excuse me, Professor Glenn, your presentation is left 5 minutes.
Okay. And so that prompts us to put ADCPs on the gliders, so we can do that in the future. We also are putting CODAR, which we'll see later on in this, to get those surface currents on the islands. So we can put that there. We've already put them in the Puerto Rico area down here to see where the currents are, so we can start watching the ocean currents that are coming in on a regular basis, because of that has that fresh water. And this is our plan to expand from Puerto Rico with the HF radar network all the way down to South America, using all the islands as stations, so we can get that surface current in. So this is another way that one of the technologies works with us. The other is to have the gliders with the ADCPs go along all the passages. And this is a very important international program where you have to get permissions from all these countries to go along that. And so that's part of the whole UNESCO piece, the UN Ocean Decade, where we can use that to be able to go, use that permission, use the decade as a reason to go visit all these countries and walk and go through their waters with the gliders, with the ADCPs on. So we started that process this year, just earlier this week. Here's glider RU-29. It's deployed in the Anegada Passage, that deepest of the passage. It has the ADCPs on it, and we'll be starting to get the real live ADCP data. It has another Navy glider flying with it as a check to all that. And then here's Luca's drifters. Just like we want to be able to see, we want to follow that surface freshwater as it goes into the Caribbean. And so when we deploy the gliders, we also deploy the surface drifters from him. So it's all working together in this case. We have a master's program in operational oceanography to start training people in how to work all these technologies so that they can be deployed. We're starting to bring the people from the Caribbean up to the US to learn how to operate them. So here's my summary. Caribbean Corridor, it's a key component of this global climate system. We get the heat transport for the climate, but we also get the hurricane intensity, which motivates a lot of our, and pays for a lot of our observations. Gliders and HF radar, they're recently added elements to the global ocean observing system. So they're there. They're part of the whole WMO program and IOC program. And so let's use them. That UN decade provides us a framework to expand partnerships so we can bring these technologies to these countries and use them as bases for important climate monitoring, in our case, hurricane forecasting. Thank you.
Thank you very much, Professor Scott Glenn, for a very insightful presentation for us. So this is very new technology for Indonesia, I think. So I think our audience here would be want to know more. And then we have, unfortunately, we only have 5 minutes for Q&A session. And please, for our audience who interested to clarify the Professor Scott Glenn presentation, please raise hand or simply typing on the chat box. There is one first question from Ibu Asmi Napitu for Professor Glenn. How applicable is a glider unit to monitor Indonesian through flow transport inferred from T and S profiles in a strait near the equator with mean flow which could exceed 2 meters per second and the geostrophic relation breaks down? Please, Professor Scott.
One of the reasons we like to put ADCPs on the gliders is to measure the currents directly. And so that's pretty important for us to do. And we know that for the hurricanes, it's one of the missing pieces because of the mixing parameterizations that we need. We need to look at the Richardson number. And without those currents, we don't have that. So putting the ADCPs on is a critical piece of that, especially gives us the shear so we can look at the mixing. For the strong currents that are going on through these passages, we do that in the Gulf Stream too, and then the loop current. And what we do is we zigzag along that Gulf Stream. And so like on the East Coast, they'll be deployed in Florida and they'll zigzag their way up north towards Massachusetts, and they'll get picked up in Massachusetts, and then they'll get redeployed and recycled like that. And so they follow the current. And so what the glider does is it uses its energy to fly perpendicular to the current, and then it uses the current to get downstream. And so every several weeks, you put another glider in and let it zigzag north, and then the next one zigzag north. And so that's how we do the sampling in those very strong currents.
Thank you, Professor Glenn. This is the second question from Pa Sydney Thurston. Is Rutgers University also accepting students from other regions of the world?
Yeah, we have a student from Bahamas right now. And we would definitely like students from Indonesia. And the BMKG Academy students are very well trained and could easily fit into this master's program.
Thank you very much. So we hope that in the near future, BMKG staff can be your students there.
Yeah, we do too.
Third question from Bayu Edo. In your experience, how effective is the use of the sea glider in shallow waters to improve ocean research?
We specialize in shallow water. We actually have more shallow water deployments than deep. And so in the shallow water that we go to, we go as shallow as 5 meters water depth. And you can adjust the pump throws for that, so you can move the pump very fast. Of course, it costs more energy. We also have a rudder, and a rudder decreases your turn radius, so you can turn much faster. And so we can actually turn in 5 meters to get back on track. And so being able to turn away from the land, so you're not always, flying towards it, is very critical when you're working in shallow water. And so different gliders have different design parameters. And if you want to be in shallow water, you really want a rudder and you want a fast pump.
Thank you, Professor. And then next question from Audia. As we know that Indonesia is surrounded by oceans, how many gliders that ideally should be put around Indonesia to get the information we need?
Yeah, we're trying to figure that out for the US too, right? And so for the hurricane season, we typically have been putting out about 60.
60?
For 60.
Okay, 60.
60 a year. And they stay out for different lengths of times, but about 60 of them go into the glider picket lines every year. Some are volunteers, they're out there for another mission, but they share their data. And so they contribute to that. Do you want more? Yeah. So there's still more work to be done to determine those things, and you have to prioritize. But for the priority regions that we have right now, about 60 is what we've been working with to start for about 3 years now.
Okay, thank you. So I think it's much more than that to monitor all our Indonesian ocean region.
Yeah, you may not know them all. You may not monitor them all. And this is just for the hurricanes.
Okay.
There's a whole nother coast.
So you have to decide which
doesn't have hurricane.
Okay, I think the last question that can be answered here in the session from Eki Amiral. Since the accuracy of weather forecast is important for us who work in operational unit in Indonesian Met Service, Is it already possible for us to measure or monitor ITF transport, maybe using this sea glider, and maybe also consider the impact of ITF transport to certain island?
Is it possible to do that? Well, yeah, I would think it is possible. It's a matter of will and where do you need to operate and where do you want to do this, and to set up those demonstration projects to see to learn how to operate in those waters and learn what hazards there are and the best way to do things.
Okay, thank you. But I think this one more question left. I think we can answer. You can answer directly here. From Nastiti Andini, dear Professor Glenn, I watch documentary films in Netflix that Sahara dust can be decreased or even block the cyclone to form. Can you explain more about this condition, and can this condition also be happen in Indonesia?
What was the condition?
The Saharan dust can decrease or
Oh.
even block the cyclone to form. Can you explain more about this condition?
I know very little about this condition.
Okay.
But I know that it's a concern, and you can see the Saharan dust come off of the continent, and it changes how, I don't know how, or I don't know how it does it, but yeah, I know it changes the hurricanes.
Okay, thank you, Professor Scotland, for your insightful responses for all of the questions. So it's time to move to second panelist, Professor Stephen Reiser from University of Washington, and floor is yours.
Okay, I'm still seeing Scott's screen here. Okay, and can I run this from my computer? Is that okay?
Go ahead, sir.
Okay. So. Can you see my screen?
Yes, we can.
Yes, perfect.
Okay. So I will go full screen mode here. Okay. So I'm going to talk about profiling float technology, which Scott touched on briefly, and how we might study the ocean circulation around Indonesia and the effect of climate. I should say that we don't have any actual floats in Indonesia or in here yet, but we are planning on doing some of the work here in the next several years through the MINTI program that is funded, and we're trying to finish the final details of getting an agreement. Professor Gordon and Professor Sprinthal talked about that yesterday. So I'm going to talk about floats and how that might work. So many of you are probably familiar with the Argo program. This is the map of Argo from today, and there are about 3,900 floats in the water. 32 countries have joined in this program, and there are about 700 floats a year deployed in order to keep this program going. My own lab at the University of Washington supplies about 110 of these floats every year. And most of those we actually build in our own labs rather than buying the finished commercial version. The typical Argo mission is profiling 0 to 2,000 meters, temperature, salinity, pressure with very good accuracies. These profiles tend to occur every 10 days. And we can go 5 or 6 years with 250 to 300 profiles. We're actually even doing better than that now in many cases. An important part of this is all the data are publicly available within 24 hours of collection. You can go to one of several sites and download the data and begin working on it within a day of when the profile is collected. So this is just many of you may have seen this before, but this is a schematic of how the floats actually work. They're at the surface. They descend to a depth of 1,000 meters. This takes typically at about 6 hours. At 1,000 meters, they drift for about 9 days. And they don't do too much while they're drifting. They don't consume a lot of energy, but one thing that one can get out of this drift is a velocity estimate at a depth of 1,000 meters. And another thing that we're going to do as part of Minty is we are able to make an estimate of wind and rainfall along this path. Even though we're 1,000 meters below the surface, we can still get an estimate of surface wind and surface rain during this 10 days. We get an estimate about once an hour. After the 9 days, the float will descend to 2,000 meters and then profile to the surface. That takes it about a little more than 6 hours. And during that profile, we'll collect a CTD profile. In Minty, we will collect an oxygen profile. We will get a chlorophyll and backscatter profile. In other experiments, we have added nitrate. We can do pH. Some people are starting to do nitrite. There are other things that we can measure. But in Minty, we're going to be doing CTD, oxygen, fluorometer, backscatter, a velocity estimate, an hourly wind and rainfall estimates. The other thing I should say is we actually have 2 CTDs on the Minty floats. The normal one that operates in Argo and a secondary one that I'll talk about here briefly that just becomes active close to the surface. So very near the sea surface, we can get very high resolution profiles of CTD. So here's what some of these floats look like. These are mostly floats built in my lab at the University of Washington. And over here on the left, the dark one here is a Navis. That's actually, we buy those from Seabird, already made, but the other ones here are, the components come from Teledyne Web, but we build these ourselves. This is the version for Argo. The SOCOM version is something we are using in the Antarctic. We have nearly 200 of these operating in the Antarctic now, all seasons of the year. They work under the sea ice, so we're able to actually collect, we've collected now over 20,000 profiles under wintertime sea ice, and we're learning a lot about what goes on in the winter in the Antarctic. This is the top of a SOCOM float. You can see there's a lot of things going on here. This is the float configuration we plan to use in Minty. So here is the oxygen sensor. It's up in the air, so when the float's on the surface, it's out of the water. This is the CTD here. There's another CTD that is, you can't see, that's behind that is the one further into the surface. This is the PAL, a passive listener that will allow us to measure wind and rain here as well. So this is what we're going to be deploying in Minty. And the other thing here on the bottom here of this float, as there is on this one, is the fluorometer and backscatter sensor. So what can you use this for? This is from a paper from my colleague Allison Gray's PhD dissertation. She is now a professor at the University of Washington, but this was when she was a PhD. She basically took all the profiles that were available, the Argo TNS profiles and velocity estimates available up through 2014. At the time, there were about 1.7 million of those, and created a map of global circulation this way. And this is absolute circulation. This is not just geostrophic circulation reference to some level. What she did here was to take the 1,000-meter velocities that we've measured from the drift of the floats and to add that to the geostrophic shear estimated from the TNS data to end up with absolute geostrophic velocity for the entire world, save for a band around the equator where the flow is not geostrophic. But everywhere else you can do this, and you can do this at every level between the surface and 1,000 meters. I've just shown the 200-meter map here for convenience, but you can clearly see the major subtropical gyres of the world ocean. Around Indonesia, it's close enough to the equator that some of this doesn't work, but we're not going to do that as part of Minty probably anyway. This is more like the kind of thing we are going to do in Minty. As I said, we don't have any floats near Indonesia yet, but this is some work in the equatorial Pacific as part of the Tropical Pacific Observing System pilot program that NOAA and several other groups have been running for a number of years now. And we have we've deployed a number of floats in the equatorial Pacific, and many of these have biogeochemical sensors on them. The ones here in color are a very similar configuration to what we're going to use in Minty. They also have a pH sensor, which works very well. We won't be using that in Minty. As you can see, some of the other ones here also have wind, rain, and pH. We actually have a ship out there, a NOAA charter vessel called the Bluefin that's out there right now, deploying some more of these up here in the Western Pacific. So have a look at this one here in the purple one, 12792, which was deployed over here and went this way. And I'll show you some more observations from that. This is an example of, on the left here, from one profile from 12792 from earlier this year. It shows you what you're going to get. You're going to get here in temperature is in blue, salinity is in red, oxygen here is in green, and chlorophyll is in this kind of yellow color here. We get a point here about every 2 meters between the surface and 2,000 meters. So there are a lot of data here. It's pretty high resolution data. And this is the kind of thing we're going to get on the Minty floats on every profile. And what can you do with that? Well, there are, of course, many things you can do with that, but here's an example of something you can do with this. This is just the upper 300 meters of this profile, but this is for the entire life of this float through June of this year. So we have 2.5 years worth of data here, basically, and we're just contouring the results of all those profiles. So you can see the evolution of temperature, the evolution of salinity, and the evolution of dissolved oxygen here. And you can clearly see here that the temperature is colder, then it gets warmer, and then somehow here especially in July of 2019, we hit a very warm patch, and then it gets colder again. And at the same time that it's getting warmer, the salinity is decreasing rather markedly. And this is, of course, due to the seasonal rainfall associated with the heating. And then if you look at the dissolved oxygen, you can see that in the summer here, the oxygen is generally relatively low, but we do have this patch here below the surface where it looks like there's likely some sort of a phytoplankton bloom going on. We haven't measured that, but I've seen this before in other places in the world, and generally these subsurface maxima that come and go are indicating that there's bloom conditions going on. So there's a lot you can learn with these floats when they've been out there over an extended period of time. So the other thing we're going to measure in Minty is rainfall and wind. And you may well ask, how can I estimate that from 1,000 meters while the float is drifting? But it turns out that the two loudest natural phenomena in the ocean are wind and rain at the surface. So much sound is generated by bubbles at the surface when it rains and when the wind blows. There's so much sound generated by that even at a depth of 1,000 meters with the proper processing techniques, you can hear that sound, and then you can invert the sound you hear to infer rain and wind. And that's what I'm showing here. Again, it's the same time as the temperature and salinity things I showed before. Here's the history of rain and wind. We actually get something once an hour. I've cut the numbers down here so you can see a little more of the behavior here, but you can see here at that same time when the salinity was going down in July of 2019, the rainfall was up. Obviously, that's the culprit for why the salinity went down. The wind is not too variable here over time. It's always usually less than 10 meters per second, but there are intervals here when the wind is high as well. And the rain and wind here are local rain and wind. So if here is a float below the surface, here's the sea surface, we're basically capturing estimates of rain and wind here from a circle on the sea surface that has about that has a diameter related to the depth of the float. So if the float is at 1,000 meters, we're basically getting something that's representative of rain and wind within a couple of kilometers of the surface expression of the float. Although a lot of work has gone into validating this against satellites and moorings, and it turns out that this is actually representative of the wind from over a considerably larger area, it appears, than what this might say. But to be conservative, this is what we're estimating. So the other thing that's on these floats, that's going to be on the Minty floats, is, as I mentioned, an auxiliary CTD near the sea surface. And this allows us to get very high resolution measurements up as little as 10 centimeters sometimes near the sea surface. This is from a float just north of Indonesia from about 10 or 11 years ago. And I've only shown here the upper 5 meters. And this float, we actually changed the mission. We can do that using the two-way satellite Iridium communication. So here we changed from a normal Argo mission to a mission where the float is just going up and down 200 meters to zero every 2 hours. And this is a map here over just a 21-day period, a 3-week period where the float was going up and down every 2 hours. And you can, and just the upper 5 meters. And you can clearly see here, there are bands here that represent basically tidal variability here in the upper 5 meters. You can especially see it in temperature. It's less evident in salinity. If you look at the frequency spectrum of this, you can see here that the temperature has a peak here at about 1 day. That's the diurnal signal in temperature. And it has another weaker peak here at about 12 hours. That's the tides. This is, of course, not the barotropic tide. It's probably the baroclinic tide running along the base of the mixed layer that has some expression near the sea surface. Salinity, interestingly enough, does not have a sharp peak at 1 day or anything near the tides, likely because what drives the diurnal cycle in temperature is directly solar driven, but salinity, to the extent there's a diurnal variation at all, and there is something in here around 24 hours, is more driven by the time dependence of convection that there is sort of a daily cycle in rainfall driven by a daily cycle in deep convection in the atmosphere, but it's not a narrowband process like the temperature driven by direct solar heating. So one other thing about this, if we look right here, you can see a dark blue line perhaps. I want to just zero in on this feature right here because there's something interesting that comes from this. This is that feature here, and I'm just showing the upper 15 meters of the ocean here. And now I'm just showing 1 day worth of data here. Not even that, a bit less than that. But you can see here, this box here is the rainfall estimated from TRIM. And you can see here around 2 o'clock universal time, there was a pulse of rainfall. This is the ocean's response to that. And so you can see here that the ocean got colder here, and more importantly, the ocean got fresher here by about 1/10 or more of a PSU associated with this relatively weak rainfall event, actually. And it took the ocean about 8 hours or so for the event to go away and come back to where we started. Now, of course, that rainfall it most likely went deeper. It mixed deeper down, and that's one of the interesting things about this is the mixing that you can see from these kind of events. We have had about 100 floats with this auxiliary CTD on them around the world, mostly in the tropics, and we literally have hundreds of events like this that we can look at. And one of my previous students, Jesse Anderson, who's now at Woods Hole, did a whole PhD dissertation on these rainfall events a few years ago, and it's turned out to be a very interesting and useful measurement to make. On the floats in Minty, we'll be able to do this, and we'll also be measuring the rainfall and the wind ourselves. So I'll just show you one other float that was around Indonesia. This one was deployed in the Eastern Indian Ocean in December of 2002, and it operated for 9 years up through December of February of 2011, much of it along the coast here of Sumatra. And you can see the full 9-year time series here of temperature and salinity associated with it. Scott mentioned barrier layers. This is a very strong barrier layer. Here you can see the mixed layer in temperature tends to be a lot deeper than the mixed layer in salinity, but the density here is controlled by the salinity. And you can see here various interannual kind of variations. Some of this is likely associated with ENSO and La Nina events that happened, or Indian Ocean dipole events that happened during that time. This is just a preview of the kind of thing we'll be able to see in Minty. So what are we going to do in Minty? This is a slide I took from Professor Gordon's talk the other day. Scott mentioned the conveyor belt. Globally, you can see all of these gyres and the amount of heat they transport. But one of the real important points is here in Indonesia, where there's the shallow flow returning from the deep conveyor, exits the Pacific and into the Indian through a number of straits here. The most important probably is Makassar Strait, but there are the other ones here. All of this water ends up, or most of it, in the Banda Sea and then is ejected into the Indian Ocean. But the stuff that comes in on this side is as measured by its temperature and salinity characteristics, and the stuff that goes out on this side as measured by its temperature and salinity characteristics is not the same. So there's a transformation of this water in the Indonesian seas, much of which happens in the Banda Sea. And that's really where we're going to concentrate our float resources. There are moorings in Minty that are going to be distributed throughout a lot of these places, but the floats we're going to concentrate in the Banda Sea to look at these mixing processes. Floats are very good for looking at mixing. They're not so good at looking for things like flow through straits and things like that, because they won't stay in the strait, but they're great for looking at things like mixing in the Banda Sea. So this is, Professor Gordon mentioned this yesterday, but here's the field campaign that's planned. We have this is sponsored by the U.S. National Science Foundation. We have moorings from Woods Hole and Scripps. We have contributions from Lamont with Professor Gordon, a modeling component at Rutgers with John Wilkin, and my group at the University of Washington, including my co-PI, Jay Yang, who's analyzing the wind and rain data, is involved as well. We have a group from BMKG with Nellie, Florida, and others. And then we hope to add a group from Australia. This is still uncertain, and we will coordinate this with some groups from China. But the goal here is to instrument these passages for several years to look at the transport from the passage, and at the same time put an array of floats here in the Banda Sea to look for the internal storage of heat for mixing and how this water mass changes from the Pacific to the Indian side, what's actually responsible for the change. So just to conclude here, I'll say that really to understand what's going on in the Indonesian seas here really is going to require measurements for many years. There's already been a lot of measurements there, and we need to continue that. Argo really is a global array to look at the large scale circulation, but the same technology can be used in some parts of the Indonesian seas, especially the Banda Sea, to look at mixing within the Banda Sea and how the water from the Pacific is transformed. And that's the plan here. The Minty floats will measure temperature, salinity, oxygen, chlorophyll, backscatter, wind speed, and rainfall. We do have other sensors that we can't put them all in the same float, but it's conceivable if we were to do more of this in the future, we could measure nitrate and pH as well. An important thing here is that all the data from these floats will be available in real time. That is, as soon as the data are transmitted by the satellite to all participants in Indonesia at BMKG and elsewhere, and to partners in the US to study the properties in and around the Banda Sea, ultimately to aid this goal of improving our knowledge of the through flow and improving models. Enough of this kind of data can surely help to improve the models of the region. Thank you very much.
Thank you very much, Professor Reiser, for very enlightening lecture. For us in Indonesia, I think Argo will be very new, and we hope that in the near future we can also participate in this international program in deploying the floats in Indonesian waters. So let's go to the QA session. We have two questions from the audience. First, from Mr. Randy Firdaus to Professor Stephen Reiser. Is the float just designed for depth of 1,000 meters more? Is there a specific float for measuring in shallow waters, or should we use sea glider for shallow water studies? Thank you.
Well, I think Scott mentioned the difference between ships and gliders and floats, and I think that floats are good for deep water. It doesn't have to be 2,000 meters deep. It could be a few hundred meters deep. But if you want to get up into shallow water of less than 100 meters, I think the gliders are probably better for that. The other thing is that when you get to shallow water, the flows tend to be faster. And whereas a glider has some ability to work and to work against the flow, floats have none of that. So if you put a float in a place where there's a very strong flow, the flow will follow the flow. These are quasi-Lagrangian, and the float will leave the area. So I think that the shallow water is best left to moorings and to gliders, whereas the deeper water floats are perhaps a better match there.
Thank you very much. The second question for you, Professor, from Bu Asmi Napitu. What the parking depth for the Minty floats will be in Banda Sea? Is it 2,000 meters or deeper? It would be interesting to profile temperature and salinity closer to the benthic layer to measure heat contents in Banda Bow. Would it be possible to attach an acoustic system to the floats measuring flow or shear, Professor?
So I'm not sure how deep the benthic layer you're talking about is. The limit of these floats is 2,000 meters. There are deeper floats that are being tested in pilot programs now to go to 6,000 meters. Those are not, we're not planning to use those here in Minty, but in this schematic diagram here, I've put 1,000 meters because that's what we usually use in Argo, but there's no need to do that. We could put that somewhere else. You could put it anywhere between 0 and 2,000. In fact, in this plot I showed here, here we parked the floats temporarily at 200 meters. So we have a lot of flexibility to do that, and we don't have to make the decision when you put the float in. We have the ability to change the mission through the satellite. Let's see, what was the other, there was another part of that question. Can you repeat that for me, please?
So,
could we put an acoustic measurement of velocity on there? We could. We have not. That has not been part of the plan here. Technically, it could be done. I should say that the floats here we're going to use in Minty are being built right now and should be finished. The construction should be done here in just a few more weeks. So even though the actual Minty deployment program has now, due to the pandemic and the lack of ships, has been postponed until early 2022, we could actually deploy the floats sometime early next year. We would be ready to do that if there were a ship to do it and people were interested. We don't have to wait for the moorings to put the floats in. So if you want to add something to these, it's kind of late to do that because they're being built right now. But in the future, if we do this again, once we've learned a little bit here from the first deployments, there's no reason we can't incorporate other technology into things we might do in the future.
Thank you, Professor. Is there any other question? Maybe one last question, because time is near to finish. Kuneli, maybe you have a comment from Professor Reiser's presentation, maybe regarding the Minty or something else.
Yeah. Thank you, Pak Riris. I think we have several discussion with Professor Steve Reiser, and I think I agree with you. We don't need to wait for the mooring for the Minty program, that we can deploy the float before the mooring are ready to deploy. Thank you, Prof.
Okay,
yes,
thank you.
and the other thing is about that is the ship that is required for moorings has to be fairly large. The ship to deploy floats is Can be anything, a fishing boat or anything.
Yeah. Okay. Yeah.
Thank you, Bu Nelly and Professor Reiser. Sorry, maybe some other audience will ask, but time is up. So I'd like again thank you for very interesting and enlightening presentation from Professor Steve Reiser. So, dear participant and panelists, so this is the end of the first session of this ocean group. Now we will have a short break for 5 minutes, and then we will uh, be here again on 9:45. So please take a short break to take a coffee or tea. Thank you very much and see you again.
Stasiun Meteorologi Kelas 2 Silangit Tapanuli Utara merupakan stasiun meteorologi penerbangan dan memiliki tugas serta kewajiban dalam penyampaian diseminasi informasi cuaca di 5 kabupaten kawasan Danau Toba.
Welcome to Silangit Meteorological Station in North Tapanuli. I am head of the Indonesian Agency for Meteorological Climatology and Geophysics Regional 1 of Medan, North Sumatra. In my right is the head of Silangit Meteorological Station. We present the profile of the Silangit Meteorological Station and Lake Toba area for all the attendants of the 15th Annual Indonesia-NOAA Partnership Workshop. Thank you. Horas, horas, horas.
shall we start again? So it's now 9:45. So we will go to the second session for this Ocean Group seminar for the third days of the 15th Annual Indonesia-US BMKG-NOAA Partnership Workshop. And firstly, I would like to introduce the next two finalists in this second session. The first is Dr. Luca Sentirioni. He is from Scripps Institution of Oceanography, University of California in San Diego, and he is very experienced in many research regarding climate, atmospheric science, and physical oceanography. His research interests in large-scale oceanic circulation and observation with Lagrangian, and then development of ocean instruments, mixed layer dynamics, and vortex dynamics. So he's going to talk about the use of drifter buoy technology to enhance Indonesia ocean models, including new directional wave spectra drifters. So it's also new technology for us in Indonesia, and I think in the near future, we'd like also to apply this technology. So this is good opportunity for us, for Indonesian colleagues, to learn from Dr. Centurioni today. And then the second panelist would be Professor Eric Terrell from the same institution as Dr. Centurioni. Professor Eric Terrell is Director for Coastal Observing Research and Development Center in Marine Physical Laboratory, Scripps Institution of Oceanography, University of California in San Diego. He also served as a technical director for Southern California Coastal Ocean Observing System, SCCOOS. So it is really happy to have Professor Terrell to share us about the HF radar networks and how it works, how to manage that, because we are in Indonesia, just has at least 4 HS radar, and then we will expand more in the near future. And this is good opportunity also for us to learn more about this from you. So, dear audience, let's begin with the third lecture today with Dr. Luca Centurioni. So, Dr. Centurioni, floor is yours.
Thank you very much. Let me share my screen. Okay.
Yes, great.
Okay, thank you very much for inviting me again. So I like to change gear. We've seen from the presentations from Steve and Scott how you measure below the surface. And I like now to talk about how we can actually measure important parameters for oceanography and atmospheric science at the surface. The drifters you'll see today are a little bit different. We operate on a much faster time scale. So to give an example, Argo floats, as Steve mentioned, they come up to the surface every 10 days. Drifters are operating on a 1-hour cycle. So they measure much, much faster, because now we are concerned with timescales, which are a little bit different. And when you want to measure things like tropical storms or weather system, you need to sample much more frequently. So I'm Luca Centurioni, director of the Lagrangian Drifter Laboratory and of the Global Drifter Program. And what you see in those slides are a couple of examples of deployments. You see in the center picture, this is a wave buoy that is being deployed near Iceland to measure, very large waves that occur over there. What you see here on the right is a little animation showing air deployment of drifters ahead of tropical storms, and in this specific case, a hurricane. So we do that because essentially when you're measuring at the interface between the ocean and the atmosphere, you become capable of observing parameters that can actually be very useful to determining the heat flux or the entropy fluxes from the ocean into the atmosphere. And you measure, for instance, variables that are dictating the intensification of tropical cyclones. Let me move to the core of my presentation. This is a slide that shows or summarizes what the Global Drifter Program is about. What you see in this map to the left is a snapshot of our array as of a little more than a week ago. And as you will notice, we have a global coverage. And you see dots of different colors. The red ones are representing drifters that are measuring the sea surface temperature. And we do that because all the satellites that are measuring sea surface temperature still need to be calibrated or validated against in situ measurement. So the Global Drifter Program is the only in situ network that provides those background measurements for constraining the accuracy of satellite SST. Although we are a scientific program, we are so spread out globally that we have an operational component that provides that in real time. So drifter data are available within 15 minutes from collection, and they're distributed globally, as I just said, for calibrating and validating satellite. However, the other very important thing we do, and this is represented by the blue dots that you see in this map, is to measure atmospheric pressure at sea level. And as you will see a little bit later, that has a profound influence on weather forecasting. So those sea level pressure data collected in locations where there is essentially none, because yes, ships are measuring sea level pressure, but number one, those observations are less accurate because the height of the barometer is not always well known. And number two, ships operate on very specific commercial lanes. So we do collect observations like, for example, in the Southern Ocean, where essentially there is none. And I'll show you an example on how impactful those observations are. So as I mentioned before, we are essentially a scientific program, so we like to support scientific publication in peer-reviewed journals, and the GDP has collected over 1,100 papers that are published using the drifter data. Let me just give you a little snapshot of what is happening in the Indian Ocean before moving specific to the technology and what we do with BMKG in Indonesia. As you can imagine, to maintain a global array of this extent, we need to collaborate with many partners around the world. And this is done within an organism that is called Data Buoy Cooperation Panel, which is part of the World Meteorological Organization. And we divide the world's ocean in sectors. And there is a specific subpanel within DBCP that takes care of the Indian Ocean. And so as you see, we have a target that calls for sustaining a network of 150 drifters with barometers and sea surface temperature, and 265 drifters with just sea surface temperature. And what you see in this picture to the right is the progression through the years, starting from 2007, starting from 1996 up to 2007. But there is the effort is continuing. And in red, we are representing the barometer drifters number, and in blue, the sorry, in red, the sea surface temperature drifter number, and in blue, the, sorry, it's the other way around. It's confusing because the dots are coded differently. So in red, the sea level pressure drifter number, and in blue, the sea surface temperature drifter number. You will notice that starting in 2014, there was a big increase in drifter numbers in the Indian Ocean, and that is because we led, as part of the Lagrangian Drifter Lab, several scientific programs in the region that allowed us to dramatically increase our presence in the Indian Ocean. A few words about the drifter technology. This is the basic drifter we deploy throughout the world. Remember, this is represented by the blue dots in the global map. And this specific drifter it has a sea surface temperature sensor and a barometer. So those are sensors of scientific quality. So they're very accurate and very stable. So they don't drift much through the years. The drog, which is represented by the purple cylinder here, is essentially a sea anchor. And this is fundamental for the drifter to behave as a Lagrangian instrument. And by Lagrangian, I mean a drifter that is able to follow the water very carefully. And so without that, the drifter will be pretty much influenced by surface waves and wind, and will fail as a Lagrangian current meter. And again, Lagrangian here is intended as a water following device. There are, throughout the years, we deployed over 25,000 drifters globally. And the data are open and available in real time to the entire world community. We have drifters of many different configurations, and a few examples, which, by the way, is not at all comprehensive. You can visit our website to get an idea how many configurations we have. But four differences are presented in the slide. You see on the top left what we call the salinity drifter. And this was used in several NASA-funded experiments to study sea surface salinity. So this drifter is equipped with a seabird sensor, same that is used on the Argo floats. And it can measure surface salinity every 30 minutes. And it was used to correlate the distribution and the evolution of sea surface salinity as a function of rain. What you see right below is what we call the Minimet, which can also be configured with a long thermistor chain. And this instrument is used to measure the surface wind. You see it carries a wind sonic anemometer. It has a wind vane that will help measuring the wind direction. And it has a barometer, a sea surface temperature, and either a drog to become a Lagrangian instrument, or a very long thermistor chain up to 200 meters that carries temperature and pressure sensors. And this is used to measure the heat content ahead of hurricanes. What you see on the right bottom corner is the newly developed instrument, which was developed starting more than 10 years ago. And we call it the directional wave spectral drifter. This wave drifter is measuring surface waves every 30 minutes and returns the full spectra, the three-dimensional spectra of the waves. And I will talk a little bit more in details about those observations because they are very important for wave forecasting and also for scientific research. On the top right is a little drifter that we use for observation within rivers and estuaries. This is a very sophisticated drifter that measures simultaneously waves, the depth of the bottom, or the depth of the water, and it also carries an ADCP, so it actually gives you not only surface currents, but a full 3D profile below the drifter. Few words about wave observation. So waves, global wave observation are becoming extremely important for not only forecasting, but also for the Earth's interaction science. Things like surface roughness and wind stress are depending on waves. And so it is important to have a very good understanding on how waves are distributed globally. What you see right at the center is a modification of the wave buoy. This one was developed about 3 years ago, and it also has a barometer. So this instrument is measuring simultaneously air pressure and surface waves, including spectra. We have deployed very many globally as a pilot array. We're increasing our global footprint. And this buoy was tested very carefully against well-known instruments like the data well. The beauty of the wave buoy that we make at LDL is that it's much less expensive than a full-size data well. So that allows us essentially to maintain a global array of wave buoy. So you see deployments in the Gulf Stream right here. We started in 2019. We partnered with the US Coast Guard to maintain time series in the Gulf Stream. We deployed in the Pacific Ocean, in the Indian Ocean, in the Southern Ocean. And what you see in the center plot is a trajectory of a wave buoy that was deployed in the Southern Ocean. And the significant wave height is shown right underneath in blue. And the red line is showing model data from WaveWatch 3, which is run by NOAA. So you will see that for the most part, the agreement is very good, but there are times when the difference is significant. So as we deploy more and more wave drifters, we are trying to rationalize why there are such differences at times, and why there is such a good agreement at other times. And you have to keep in mind that there are all sorts of interactions going on in the open ocean, like wave currents interaction, waves interacting with eddies, and not always the wind speed and direction is correct. So the model may actually show different values compared to observations. So we are working with several colleagues and students of mine to make sense of those differences. All the wave buoys are fitted with Iridium technology. That is a two-way telemetry system, which allows us to change the mission and the way, so we can decide to have the wave buoy sampling faster, slower, and that also allows us to transmit the full wave spectra over the air. We are also working in close collaboration with forecasters around the world to make sure that the wave drifter data can be assimilated in forecasting models and also used for hindcast studies. So this is a very important component of our work to show how useful those data are. Now, let's talk about what we do in collaboration with BMKG and how well we have sampled the Indonesian region through the years. So the Global Drifter Program is probably the oldest global observing system. It started over 40 years ago. And through the years, you see we deployed very many drifters in the Western Pacific, South China Sea, and Eastern Indian Ocean. So the light gray dots that are essentially filling, becoming solid in the Western Pacific, in the South China Sea, in the Indian Ocean, are from our historic archive. And you see we had very many drifters deployed in the South China Sea, coming to the Karimata Strait. And so we had a very good coverage in the Sulu Sea, and fewer drifters made it into the Banda Sea. So I think we have an opportunity, and it was very interesting to hear from Steve about the MINT program. We could increase our partnership with BMKG and try to maintain time series of drifters or deploying drifters on a regular basis in the region, so we can actually fill this gap, which is one of the few we have in the region. So it will be very interesting to fill this void, and I'll show you what the implications could be for weather forecasting as well. In terms of collaboration with BMKG and within the Rama cruise scenario, the black dots are representing deployments of drifters from Rama cruise stations, and in red, you see the trajectories the drifter deployed within that collaboration. As I mentioned before, but it doesn't hurt to repeat, all those data are available in real time through a variety of ways, including the global telecommunication system. So they can be assimilated in forecasting model in real time, as I said, with a delay of 15 minutes at most. So here's why it's very important to measure atmospheric pressure globally and in the region. So a few years ago, starting in 2015, we ran a couple of studies together with EASTN and WF to evaluate the impact of air pressure observations from drifters in numerical weather forecasting. The plot I'm showing here is coming actually from an adjoint model, although we also did a full OSC data denial study. And you see that in terms of impact per observations, in a global domain, drifter data are the most impactful data in, between or among the entire observed system, oceanic and atmospheric. This plot is new, was obtained on 8th of September 2019, and is created by NASA. So they have a division that inspects the impact of the observations in numerical weather prediction. And it hasn't changed for many, many years. So drifter consistently are the #1 observing system that constrain numerical weather prediction. So by working, and there are a few papers published, one is shown here that you can read, and I'm happy to talk to you about that. And this is so important that we keep working with WMO to maintain a very strong presence of barometer drifters throughout the world. So something like that in the Banda Sea combined with sea surface temperature measurement could be very, very important for improving the forecasting around Indonesia. You can check, those maps following the link below. Now, the other important thing of the drifters are the velocity observations. This is more like a research mode. And I'm showing here a couple examples of scientific papers we published recently or in the last decade. And here to the left, I'm showing the comparison of ocean currents from drifters with ROMs. So we've done it for several models. And there are several techniques that we developed that combine drifting buoy data with satellite altimetry and wind, either forecast or reanalysis, that allow you to actually validate ocean models. So for instance, if you want to understand how good is your ocean model regional around the Indonesian Sea, we can think of increasing the deployments, targeting specific locations. And then you can look into statistics that would allow you to evaluate your numerical simulation and what you may want to change or do a little bit different to improve your results. To the right is another figure that is from a paper published by Verena and in collaboration with Arnold and myself last year. And this shows a study that wanted to better understand the export pathways of fresh water from the Bay of Bengal into the Arabian Sea and into the equatorial and in the southern hemisphere. So working together with Arnold and Verena, we were able to identify the seasonal variation of those export pathways And you see there is one just south of Sri Lanka, and then there is a seasonal one that essentially goes into the southern hemisphere and right in front of Indonesia. So all those things are becoming more and more possible as we work together with international partners, India, Indonesia, BMKG, to maintain a strong drifter presence in the region. So those are two of the very many, because as I mentioned before, we have more than 1,000 papers published on ocean currents, of the many things that have been addressed through the years and that will be continued to address in the future. Our partnership with Indonesia recently was enriched with the deployment of wave buoys. So we sent 3 to BMKG, 10 more were sent to be deployed from a Rama cruise. And you see a few tracks of wave drifters being deployed as of last year from Rama cruise and by Indonesia. And as I mentioned before, what I'm showing underneath are the wave buoy data. This is against significant wave height against wave watch 3 in orange. And again, you see the good agreement in generally, but with important differences. And in terms of dominant direction, remember the wave drifter is measuring the directional properties of waves. That is not so good. And so, as I mentioned before, there could be differences due to the detail of the model, how the wind is inserted into the model, and of course, other interactions due to ocean currents and eddies. So this is something we are very keen to explore with our Indonesian colleagues and increase our collaboration with them. I want to leave time for questions, so let me jump to conclusions, and we can talk more in the question and answer session. So for more than 40 years, actually, about 45, the GDP, which is a size drifter program, has been committed to provide sustained global observation of surface currents, but also sea surface temperature, atmospheric pressure, and waves. So the partnership, the global partnership with countries around the world is fundamental for our operation, and BMKG has allowed deployment of SUV drifters in many of the critical regions in the world ocean, and we want to continue this important collaboration. The drifter data have a large positive impacts for scientific applications, so many papers have been published and many more will be published, both globally and in regional context to, for instance, validate global models, understanding what could be improved. And the final point, because we have such a large global data set, is that because drifter data are open, freely accessible, and available in real time, they're used by forecasting centers. And there's a large impact for numerical weather prediction, calibration and validation of sea surface temperature from satellites. And as also Scott mentioned before, the hurricane or extreme event component is one thing we also do, and will help us better understand extreme events like hurricanes and atmospheric river and other important phenomena. So let me stop here, and thank you very much for your attention.
Thank you very much, Dr. Riani. I'm sorry, maybe I got the small problem in connection, so I moved to my cell phone. So maybe Pak Arif can assist me to read the questions for Dr. Riani that written in the chat. So we have 7 minutes for Q&A. So please, dear audience who have questions for Dr. Riani. Mas Arif can assist me to read the question maybe in the chat box.
Okay, should I start answering the question? I can see them.
Okay, from Ibu Asmi, how big is the impact of drifter drop on the quality of temperature and flow measurement above and below it? It is quite long, and I presume that it would cause shear flow around it. Please, Dr. Centurioni.
Yes, thank you. That's a very interesting question, and you have a good point. So we must remember that drifters operate on purpose on the mixed layer. So in very exceptional circumstances, yes, there is quite a bit of stratification, especially in regions like the tropical Pacific, Eastern Pacific, or the Bay of Bengal, where, for instance, a very shallow fresh layer can be associated with strong temporal gradients. But for the most part, in a global context, we operate by definition in the mixed layer. So by and large, the fact that there is a drag is not adding, it's not introducing a distortion in our measurement. So the water is very well mixed. And so we are actually measuring sea surface temperature on purpose at the location that is most useful for satellite calibration and validation. So it can be, it needs to be treated with care at certain location, but by and large, that is not a problem.
Okay, and then the second question from Pak Furkon. You mentioned that the significant wave from drifter lower than model wave watch 3. Which one is the real data? Significant wave from with wave watch 3 or drifter data? Or you can explain why the drifter data lower. How about the weight of drifter?
Yes, thank you again for this excellent question. So it's not always lower. Sometimes it's actually higher. So we like to believe that the observations are the real or the benchmark, and we tend to believe so because of all the testing we've done. So we know that the wave drifter is an accurate instrument. There are many reasons why we see differences in wave height and also wave direction. And remember, the model, wave watch 3, does not have an ocean in terms of currents and eddies. So certainly wave current interaction, wave eddy interaction can be a factor for differences. And so basically, the model is projecting waves at a slightly different location compared to where the drifter is. So that could be a possible explanation. But as I said, I have students and collaborators we are working together with to try to understand what could be the cause of such difference. Now, the second part of the question is about the weight of the drifter. Now, this is not really a problem because the drifter is floating at the ocean surface. So it's essentially a wave rider. In fact, the sphere is one of the best shapes to follow waves. And the size and the weight of the drifter is such that we can resolve short period waves, like 2 seconds wind waves, up to large swell of the order of 20 seconds. So we have an advantage over the very large data well buoy that has a diameter of about 1 meter. So in certain circumstances, it can be a little bit of a different wave rider. So that is not an issue for us.
Thank you, Dr. Centurioni. And the last question, maybe we still can answer this directly. I have several questions regarding future challenges. This is question from Mr. Hafid Pratama. I have several questions regarding future challenges related to the development of the buoy drifter data for research and improvement of ocean models, especially in regional areas in Indonesia. Is it possible that the directional spectral wave can be used in the assimilation of models such as WaveWatch 3 or SWAN? Does the required process require data quality control first?
Okay, thank you, Mr. Pratama. Again, excellent question. So one thing that I mentioned very briefly during my presentation is that all the drifter data, including the directional spectral wave drifter data, are also available operationally. So we post them to the global telecommunication system, and so they are available in real time to forecasters. Now, of course, this is only one part of the problem. And, you know, some people don't like to use GTS, so we also provide data using different real-time protocols. So there is a choice there. So if you're able to do GTS, you already are able to see the data. And please contact me so I can direct you or help you making sure you access all the available data. The data simulation of drift wave observations in models, I think, is changing depending on the processing center. For instance, I think ECNWF is probably quite advanced on that, and they can already do it. NOAA is getting ready to do it. The details of the data simulations are really specific to your system. But the answer is absolutely yes. Data are available and can be assimilated. Now, when it comes to quality control, the same issue presents for sea surface temperature, atmospheric pressure, ocean currents, if you can do it. And the same is true for waves. So what is normally done is a minimal quality control after posting to the GTS. WMO requires that the data are provided in raw form, so you don't really want to touch it too much. Now, the models normally, or the DA, the data simulation scheme, has built-in safety features to reject gross error. So say there is a spike, that of course it occurs. You should be able to have a safety feature that allows you to discard that. So yes, the answer to the question is yes. You will need to do a little bit of quality control first, but the guidelines are that should not be overwhelming.
Thank you, Dr. Sentireni. So I think I missed the last question because I just moved to my laptop because of the lost connection. Can you?
Yes, I can read the question.
Okay.
This is, excuse me, from Sandra. Question to Dr. Centurioni: is there any drifter data to be used to validate satellite-derived SST, SSS, and current in the southern Java coast for the South Java current and upwelling studies purposes, where it can be found and downloaded? All right, so thank you, Sandra. I don't have the map in front of me. If I recall correctly, the Java Sea and that particular region is again one of them that does not quite welcome drifters that tend to be ejected very quickly. So again, this is an example of a place where we can partner and deploy new drifters. So I'm very happy to talk about it, and myself and Sid Thurston can be very helpful. So let me take a look, and if you want to email me separately, I can provide you with the historical data set. And so we see what is in there at the time. And then we can, of course, we can, you can work with those data as you wish. And then we can also think about how to improve the footprint of the Global Drifter program in the Java Sea.
Thank you very much, Dr. Luca. So I think that's all the questions. So maybe from me, my quick question for you, because this is really promising equipment that we can operate in Indonesian waters. Since from your presentation, it has shown that inner seas of Indonesia still lack of this observation. Is it not so expensive to operate this drifter? And then how long is the lifetime of usually one drifter once deployed? and how long it lasts in the water?
So thank you. I think the fact that the Global Drifter program has been around for more than 40 years speaks volume for sustainability. So the drifters are extremely cost effective, and they are not expensive per se. So we're talking about a few $1,000s, something ranging from $1,000 to $3,000 per drifter.
Yep.
So it's totally sustainable and approachable. The lifetime. So in ideal conditions, like say in the southern, and when I say ideal condition, I mean away from land. Say take for example the Southern Ocean that is very rough. Waves in the Southern Ocean can be 12 meters. Very stormy region. But we had drifters going around Antarctica twice, so they lasted for up to 6-7 years, and they carried on a beautiful mission. So the average lifetime of a drifter is about 2 years when you measure sea surface temperature and atmospheric pressure. So you imagine, you invest $2,000-3,000, you get 2 years of data. So that's very good. Of course, drifters move. So in regions like Java Sea and other places where there are strong currents, like the Kuroshio, you need to keep deploying drifters because they are ejected. But this is the whole purpose of the drifters, because you want to measure ocean currents in a Lagrangian sense. So you need them to move with ocean currents. Otherwise, you fail your purpose. Wave buoys are lasting anything from 3 months to 1.5 years. It really depends on how often you measure waves. So if you go very fast and measure wave every 3 hours, 30 minutes, then the lifetime is decreased. If you slow it down and measure every 3 hours, then you can go up to 1 year or longer. So all those considerations really depend on the application and how long you want the drifter to be useful for you. So there is not a single answer to that question, but general guidelines are anything between 3 months to 3-4 years.
Okay, thank you very much, Dr. Centurioni. So time is up, I think. So again, thank you very much for wonderful explanation regarding the drifter. I hope Indonesia can also contribute more in near future, because we just starting the big project, especially for strengthening our marine meteorology in Indonesia. So again, thank you, Dr. Centurioni.
My pleasure. Thanks for having me.
Okay, dear participant and the audience, we come to the last panelist for today. It will be Professor Eric Terrell from Script also. So you will have 30 minutes in total, including presentation and QA. So please, Professor Terrell, the floor is yours.
Okay, thank you very much. And just is my screen being shared right now? Can you see my presentation?
Great.
First slide. Oh, perfect. Well, thank you very much both to my colleagues on the East Coast who are up late at night, and to our friends and colleagues in Indonesia for joining us on this joint workshop here. It's been a lot of fun listening in on many of the talks, and great to see the large number of participants, even though we are remotely shuttered here. Before I get going, I really should acknowledge that the body of work I will be talking about really is a compendium, not only of team members within our group, many of who are signed on here to help with some of the panel Q&A at the end, but a broader high frequency radar community that exists within the United States and now internationally. So we will, again, just want to extend my thanks to all those. So my name is Eric Terrell, as I was introduced, and I've been asked today to speak some to really sort of the development of a high frequency radar network in the United States and some of the lessons learned and how operationally we transitioned from the research to operations, some of the quality assurance issues and quality control issues that are ongoing. And this body of work, by and large, has been sponsored by NOAA through the Integrated Ocean Observing System and many of the regional teams here that are distributed around the U.S. Just as a very short preface, I don't think I have to go into too many details for this audience, but high frequency radar is a remote sensing technique that leverages bragg scatter off the ocean surface waves to measure the Doppler return from which we can interpret for mapping ocean surface currents. And it's really brought about the capability by having distributed antennas along the shoreline, and the frequency of transmission dictates that wavelength of ocean wave that we bragg scatter from. And so you see in these pictures somewhat of the different antenna styles. On the left-hand side is a view of the Scripps Pier, and in the foreground is a receive antenna from a CODAR system, and just to the right of it is a phased array type system that's manufactured by a company called WIRA. So there are a few different types of systems, and you can see here how you need more real estate for the phased array style antenna systems as opposed to the compact direction finding systems. But we've had a lot of growth in the last couple of decades of maturing the high frequency radar network. And this is just a snapshot on the right-hand side of the amount of coverage of high frequency derived, radar derived ocean surface currents that we resolve on an hourly basis and have an operational tool set to access these data. So the network, kind of in a nutshell, there's over 30 institutions within the Integrated Ocean Observing System that integrates these different systems. There's a data architecture that's been developed at Scripps, initially under National Science Foundation and then adopted by NOAA. And Lisa Hazard, who I believe is on the call, actually represents, is a US representative to the GEO program as we look to expand collaborations internationally in the use of high frequency radar to map ocean currents. And there is a wide consumer base within, or referred to as stakeholders of how these data are used, whether it's search and rescue or oil spill and water quality and marine fisheries. Many of the operational applications of oceanography really find themselves using the real-time data that comes from the mapping of ocean currents by this technique. So my talk overview is really to go through the quality assurance and some of the issues that we've developed here in the United States related to kind of a pragmatic approach to what the training and requirements are for the types of personnel to develop a operational system, the quality control of those data and some of the applications, and to kind of map out some of the kind of the legacy of the system and where we are today. If we were to just graph the number of radar systems that actually report into this data network, you can see the growth of it over time to where we are in 2020. We're exceeding 160 radar sites that are all feeding into a distributed data network and available in real time, both through NOAA and through a portal at Scripps to access these data, and in real-time use by our U.S. Coast Guard, as well as our NOAA, different line offices within NOAA to provide the operational oil spill response maps. So these data, we're very proud that they're used within many mission agencies to address oceanographic incidents at sea. And then these data, since they are developed by a kind of a cadre of oceanographic institutions around the United States, there's quite a bit of ongoing research with these data, and graduate students and researchers continue to work with these data. So I think a fair statement to say is really the primary QA/QC asset is the people of the organization. And there's been a rigorous training process over the years to really kind of foster the development of personnel that support this program. In 2009, a national plan was developed that really established the framework for our program. These are all documents that are available online. So, we encourage places outside of the U.S. that are looking at developing and adopting high-frequency radar to feel free to look to us as a resource to learn from many of the mistakes that we had over the years, to kind of learn from kind of a way to develop the workforce and understanding kind of the different protocols needed to make the system kind of deliver data in a very consistent manner. And kind of an outcome of this report was really we needed to have this workforce. I think we heard Scott Glenn speak earlier, his educational programs that he's provided leadership in for operational oceanography has been generating the workforce that we know is recognized here within the U.S. to maintain the observing systems. So many of the staff requirements, I think as countries look to develop systems, the cost of ownership is always paramount, and many of those sort of ongoing costs aren't the hardware, but the personnel costs associated with keeping a network alive. And the kind of a bottom line up front is that we felt that after years of experience of operating these systems for research purposes, that we felt that for every 7 of the direction finding systems or the CODAR systems, we needed about 2 FTE attached to it. And for the phased array systems, because of the additional complexity associated with maintaining the antenna arrays, the feeling was from the groups that we had worked with that operated those systems in the US that they probably needed about 2 personnel only for 4 systems. So there was a cost efficiency associated with working with the direction finding systems. And this just has to do with the efficiency of operating those 2 different types of systems that have different modalities of sensing and complexity attached to them. I'm not going to read this list here, but suffice to say there is a number of requirements that we felt that sort of laid out a work plan for the types of activities that technical staff would be involved in. And in regards to personnel training, in 2005, we established as a community the Radio Wave Operator Working Group. And really the charter of that was to foster the collaboration. So lessons learned in one organization could be shared with others. And there's an annual meeting that happens in the United States. And there's also a forum so that as new personnel come online, they can write the broader community supported by this NOAA operationally funded network to get background on all the various aspects of both setting up a site or maintaining or the management and processing, as well as some of the theory. Each radio wave working group annually has a theory-based program at the beginning. And then we always recommend, highly recommend that all technicians undergo the manufacturer-provided training that's associated with their particular technology. But as a network, we're agnostic to the manufacturer's information. We start with a data format that then is propagated through the network. We also established a technical advisory group in the United States, and this really provides direction on the elements of high frequency radar research and development, and it's an interagency group and it reports to the NOAA IU's office. And this identified a number of techniques that needed to be addressed and further matured, both in the algorithm developments as well as what types of data should be archived in the long run. So just like you have in satellite missions, level 1, level 2, level 3 processing, we felt very similar with the high frequency radar data. And how do we work with NOAA's data centers for archiving those information? We also established a best practices in 2008, and this has been continually updated that really identified deployment and maintenance of these antenna networks along the US. It was initially developed here locally at Scripps in response to a $21 million investment that the state of California had. So the onus was on us to keep these systems operating. And then we adopted that throughout the US with the initial California state investment. And a lot of that covered issues such as site locations and off-grid power supplies, remote operations on islands, much of it very apropos to the challenges Indonesia has for sighting radars. Some of the very basic logistics attached to an antenna, optimal site is for the ground wave coupling to keep the radar antenna technology near the shoreline, so you get a good ground wave connection with the the conductive sea surface, having a wide area field of view, and power and network availability. Those last two are really turn out to be many of the challenges associated with maintenance of the system. Some of, just anecdotally, some of the sites we've had running on islands that are solar powered are more reliable than grid-based systems that we have here, at least that I've operated here in the US and overseas. So some of the another example is like siting the antennas. These just give you kind of the diversity of systems. In the lower right, this is University of Alaska Fairbanks had a skid-mounted system that was both wind and solar powered. And the upper left is an image from the San Clemente Island with a radar up on the island top. One element of ensuring from a direction finding perspective, a very strong antenna beam pattern, and a measurement campaign that documents that. So this upper left curve, this is the two dipoles that are associated with the direction finding elements of the system. And beneath that image this is an ideal picture on the top, and below it is a measured beam pattern. So we decided it really recommended to measure that twice a year. And historically, this required taking out boats, costly, just kind of logistically burdensome effort of bringing a vessel out and driving. Many times it was a multi-day process to have a transponder in the field of view of the radar. And now with the modernization of low-cost unmanned aerial systems, we're able to fly that beam pattern directly, knock those out in a day. So in the operational quality control associated with mapping the totals, the RTV, this is the real-time vector. This is a little bit of an eye chart of text, but really to suffice to say is that we have a variety of methodologies for aggregating these data and ensuring that when, say, for example, an oil spill happens, that we've got a methodology that works in a fault-tolerant network to get these data to the right users. At the site level, these are some issues the manufacturer provides. So in this case, this is the CODAR C-Sonde. On the right-hand side, we see a Bragg scatter Doppler spectrum. So there's the Doppler spectrum, and the two peaks are the first-order Bragg scatter return. This is the information at these peak areas that are used to resolve ocean surface currents. Within our network, we've developed a number of network and site diagnostics to make it much easier to remotely manage a large number of systems. In this case here, the green dots indicate the radar is operating as it should. The red dot indicates it's offline, and a yellow dot means it might need some attention. And a user can interface into any one of these locations and pull up a variety of quality control information indicating the performance of the radar. And this is part of the national network. So a manager on the West Coast can look at the East Coast radar data in the same way as an East Coast radar operator. So it allows a distributed network of personnel. So again, thinking about other areas of the world where you'll have a distributed workforce that maybe is working at different time zones, this kind of architecture has worked well. So to give you an example now of some of the quality control research underway, my colleague Lucas Santoroni talked about the use of drifters for measuring currents, amongst other things. And on the left-hand side here, we see a map of ocean surface currents. And we are just looking at the using those ocean currents to indicate the set and drift of parcels of water as they disperse and advect through the water column at the surface, or advect at the water surface. And this sort of is the kind of the premise by which a study was done with one of my colleagues, Carter Ullman, who had time and again released many drifters within the field of view of these radars, and then looked at the velocities of these surface drifters relative to velocities as measured by the HF radar. And this is the scatter plot that we see on the right-hand side. Much of this scatter is often attributed to the sub-grid scale variation that we see at the ocean surface that's not captured by the radar. So the radars are an integrated measurement on the scale of a 1 to several square kilometers, and an individual drifter might be under the influence of internal waves or fronts that are subgrid scale. Suffice to say, though, that the technology, the U.S. Coast Guard uses it almost exclusively to improve their search and rescue operations. Oops. Another example of quality control research happening here at Scripps. This is with a colleague, Sophia Merrifield. She's been working with the Office of Naval Research on a HF radar array that's been deployed in the Republic of Palau. So this is operating now in an area much closer to Indonesia, and looking at the flow relative to NEC and NECC. And on the left-hand side, we see kind of a snapshot of current flow. This is the island group of Palau, whether it's in the wake or in the lee of the general synoptic flow in the region, and the variation that we see here in the maps of ocean currents associated with that. These are 3 sites that are distributed along the shoreline. A 4th is expected to be deployed soon. Looking a little further at those data on the left-hand side, so under the sort of impetus to use geophysical interpretation of the data to guide our quality control, one thing that can be done is to look at the spectral content of the information. So the left-hand plots in the upper left are the UNV components of the mooring data, as well as the HF radar data. And you can see the good agreement. This is the uppermost bins of the HF radar. And as you look at the velocity spectral content, you see quite clearly the lines associated. So these are the rotational spectra of the velocity information from the HF radar data, as well as the mooring data. And you can see the distinct lines there that we see at the tides, the diurnal and semi-diurnal components, as well as the low frequency content within the flow that's reflected in both of those. And if we're to look on the right-hand side, we now see a vertical section where we had a mooring deployed for over a 12-month window. And it's really quite fascinating. The very top slice here indicates the UNV velocity components as measured by the HF radar over that mooring. And you see how the interior of the ocean varies as a function of time. And really the take-home message here is that obviously surface currents don't reflect what's happening throughout the entire water column of the ocean, but you do see here when the interior of the ocean is influencing the surface currents. On the right-hand side actually is a look at the correlation coefficient as a function of depth. So this was 2 separate moorings or 2 separate current meters or ECPs on a wire extending down to 700 meters. And so because of the stratification, you really have this multiple layering of the ocean.
Excuse me, Dr. Terrell, you have 2 minutes left.
Perfect, right on time. So some of the applications now, just to wrap up, this is an example of an oil spill in Santa Barbara, California, and the HF radar data was used here by the U.S. Coast Guard to guide where booms should be placed to contain that oil spill. We've had a number of national responses in the U.S., both from the Costco Busan off of San Francisco, the Refugio, and various search and rescue, the Deepwater Horizon spill, and again, search and rescue operations on the East Coast as well. These are some applications with ocean color. So looking at the fusion of ocean color information with high frequency radar. This is provided to me by Marco Tero. So these data complement the surface currents with the water quality and water constituents. As well as water quality discharge maps are routinely used for some of the water quality prediction issues. The last thing I wanted to ask Sydney, talked a little bit with Sydney, the issue, BMKG has visited a number of times, interested in the use of unmanned systems, and Scripps recently announced a partnership last month with NOAA for partnering to develop unmanned systems research here at Scripps, and really to look at how do we transition research to operations with these types of systems. And one example is the use of the wave-powered surface glider called a wave glider, and research is being done now running transits out to 200 nautical miles and back along historical fisheries-based research lines called the Coffee Program. and collecting information at wave buoys as well as at meteorological NDVC operated buoys, and looking at the quality of information coming from the wave glider relative to these standard moored assets. So my last slide, again, thank you very much. Look forward to continued collaboration with BMKG, and like everybody, looking forward to the travel bans to be lifted. Thank you.
Thank you very much, Dr. Terrell, for a very wonderful presentation, and it's really enlightening us regarding the recent advancements in HF radar technology you developed in scripts. So it's look like our colleagues that visiting your office, yeah?
Those are your colleagues, yes.
Yeah. So
we're always looking forward to Nelly and her team visiting.
Of course, yeah, we would like to visit in some other times. We have 5 minutes left for QA. Dr. Terrell, would you please stay and to answer the question from Randy Firdaus? Dr. Terrell, I have 2 questions for you. First, BMKG has Kodar HF radar at 2 sites, Bali Straits and Labuan Bajo, East Nusa Tenggara waters. For wave data, these 2 sites differ in terms of data availability. In Bali Strait, the wave data is almost available at all time, while in Labuan Bajo, the wave data is often missing. In a month, the wave data that we collect was often less than 40% for Labuan Bajo. Why did this happen? And the second question, is the HF radar wave data is accurate enough, as we know that HF radar mainly for ocean current measurement? Thank you.
So I get my first, I guess, comment to this, and I apologize, it's dimming here because the lights are automatically going off behind me. So,
okay.
If this is so it's a Kodar HF radar system. So one of the challenges with using the direction finding style antennas for measuring wave fields is that the Bragg return is over an integrated measurement in azimuth. Now, if you're on the section of coast that's straight with very homogeneous wave conditions, you can develop relationships between the energy return and looking at the backscatter return along this annulus that would be formed at the range ring upon which waves are derived. Now, places like within straits, within Bali or Labuan, I imagine there's quite a bit of gradient if you were to look at an annulus at that particular radar site, and what the wave information might be like as any function of angle along that annulus. And that variation as a function of angle can lead to biases. We've done studies here locally that showed that we weren't doing a very good job in areas where we had a lot of gradient in the wave field as the radar was attempting to measure it. So I think there's other ways to measure waves. Moored buoys are oftentimes the gold standard for measuring waves if you have a very place-specific problem at hand. I can realize, you've installed the radar for currents and you're getting waves for free and you want to see how good those data might be. So I think it's valuable just that mileage may vary and very site-specific, and it's good to go through a validation exercise. So I would be happy to talk more offline about some of the very specific details if there's a briefing that's been developed about those 2 sites. The second question, is the HF radar wave data accurate enough as we know? So I guess I sort of answered that already, that that some locations can have biases more than others. I think it's also important to realize that the relationships, especially in a direction finding style system, will provide bulk properties. And so if you just need to know the significant wave height, you can do a lot of things wrong and get the significant wave height right. And so if your wave application problem needs very good fidelity on the directionality or spectral content of the ocean wave field, HF radar probably, at least these style radars, probably aren't the best ones to be used.
Mm-hmm. Okay, and then the next question from Asmi Napitu, Ibu Asmi. Dr. Terrell, how significant is the correlation between HF radar measured surface currents with the currents beneath 100 meters. Is the correlation sensitive to the time scale of the currents?
So I will sound like a politician on many of these questions because it depends. So this 100-meter area, I think we would need to look a little more at the mode 1, mode 2 water column structure. So depending on where your thermocline is, that could bias significantly how the surface currents reflect at depth. And that was sort of the point of the vignette I talked to you about my colleague's work in Palau that showed how that correlation can vary as a function of depth. Much of it's driven by the overall water column response and what those mode 1, mode 2 responses may look like. And then to your point about time scale of the current, certainly if, the longer you might time average out, the internal tide bias that you might see might not be present if you're temporal averaging out that signal. Again, I'd be happy to continue this conversation offline if there's more details very specific to it, or if there's some figures of your data that you guys wish to show with us.
Great, thank you, Dr. Terrell. And then the last question maybe for this QA session from Pak Bayu Edo. Dr. Terrell, ideally, how often we need to take antenna pattern measurement for calibration? Thank you.
So, Bayu, we recommend in the United States to measure the beam patterns twice a year. And then I will caveat that if you happen to replace an antenna or replace cables, or if new infrastructure was installed near the antenna, like a fence or a building, that you should calibrate after that as well.
Mm-hmm. Okay, is there any other question? I think no. So I think it's time is enough for us in this presentation. Thank you very much, Dr. Ter, for enlightening and interesting explanation regarding HF radar, especially for quality control techniques. And then we hope that our colleagues of BMKG can consult to you and your team regarding this QC technique, because this is very crucial for us because we still newly involved in this operation of HF radar at BMKG. So again, thank you very much, and looking forward for further collaboration with your unit and script in the future. Thank you again, sir.
Thank you.
So, dear audience, we come to the conclusion of this session. So, from this morning, we have 4 panelists that already shared their expertise and knowledge to us regarding the instrumentation of marine or mid-ocean instruments that maybe in the near future we will more dealing with this kind of instruments. So we hope that the knowledge that we gain from the distinguished scientists and experts in their fields can give us more detailed information regarding these technologies in terms of ocean and meteorological instruments in this regard. So from the first presentation, Professor Scotland mentioning about the advancement in sea glider and combining with other instruments like HF radar, and he shared experience in managing the goose system in west coast of the US, east coast of the US, and then this is really important to monitor the climate monitoring and also for hurricane forecasting in the US. So this is very important for us also in Indonesia, that maybe 1 or 2 years from now, we will also have this kind of instrument, sea glider, that can will be operated in BMKG. And the second lecture from Professor Steve Reiser gave us
interesting idea how floats can help us to study the ocean, and we hope that the multi project that soon to be started, maybe next year, will benefit for Indonesian scientists to collaborate with US scientists to explore more in the use of Argo float and to increase the contribution of Indonesia in float monitoring, and also to operate the BMKG's float in the near future. And the third lecture from Dr. Lucas Centurioni show us that the drifter is very beneficial to help us to monitor the current, ocean current. So right now, the GDP, or Global Drifter Program, that led by Dr. Centurioni, manage all of the drifter data from all over the world, include the drifter that deployed from Indonesian waters through the partnership of US Indonesia Rama deployment. So we hope that this collaboration will be continued in the future, maybe with our colleague from Research and Development Center. Looking forward for closer relationship and then a greater use of this drifter data for research and operational in Indonesia. The last presentation from Dr. Eric Terrell show us the importance of QC in HF radar because it sends the surface current that very important for marine transportation, especially in Indonesia. We have at least 2/3 of the area covering by water, so sea transportation is very impacted from the surface current because so many accidents, especially small ships, occurred in some part of Indonesia. So this utilization of HF radar observation will be very helpful to monitor the shipping route for passenger ship in Indonesia. So hopefully we can strengthen collaboration in terms of HF radar related with script institution of oceanography in the future. So that's the conclusion of this session, and it is great to have 4 distinguished experts in this session. I would like to extend our sincere thanks to all the presenter, Professor Scotland, Professor Reiser, Professor Dr. Centurioni, Professor Terrell, to share their expertise, experience, and insightful knowledge for us today. Let us give big applause for all of our outstanding panelists today. So thank you for all of our audience for being here today and taking time to enthusiastically contributing to this ocean session. I wish you all blessed evening for our colleagues in US and in Italy, and wonderful day for Indonesian colleagues. I will return the microphone to the announcer, Ibu Sheila. All yours now. Thank you very much.
Okay, thank you very much to all the chairmen as well as to all the lecturers. So we are now towards at the end of the workshop. Thank you again for joining us. We almost near to the noon. So prior to the general lecture session, we will have a closing remarks, as mentioned earlier, delivered by Pak Sydney and also Ibu Nelly. Pak Sydney, you already with us? Pak Sydney, we are now in the closing remarks.
Yes.
Okay, thanks, God. So we still
I
have.
am here.
It's already late there.
Terima kasih.
Okay.
Terima kasih, Bu.
Okay, so we are about to hear your closing remarks. Please, time is yours.
Great. I have a brief slideshow I'd like to present. If Pa Arif could bring that up, please. While he brings that up, I'd like to thank my co-chairs, Bu Nelly and Pa Dodo. I'd also like to thank the excellent presenters from the U.S. as well as from BMKG, and especially our U.S. colleagues in the East Coast who are up at midnight tonight and have been up most of this week, as well as across the United States. So just I have to say, I think this virtual exceeded my expectations. It was very well planned by BMKG and very well executed by staff. So I just want to say a big terima kasih to everybody. And I'd like to also just take 2 or 3 minutes, to just to go over where we've been and where we're going to go. So this is just a very short retrospective. I think people will have fun with this. We've been working hard all week, and I just want to lighten up now and have some fun. We heard from Admiral Gallaudet, the Deputy Administrator of NOAA, that the BMKG-NOAA partnership is a national treasure. He used the word national treasure. And we heard from U.S. Ambassador Joseph Donovan last year in Bogor, that our partnership is, the longest running and most valued S&T bilateral between U.S. and Indonesia. So let's take just a couple seconds here and just see where we've been. Next, this is our workshop in Bogor. You can see U.S. Ambassador Joseph Donovan and Bu Rita. Next, please. And can you all see the title of this? I can't see it on mine. Can you see that, Pa Arif, the title?
A New World? Yes.
Is it clear to you? Good, okay. But the bottom line here is, we're really at a pivotal stage in oceanography, climate, weather forecasting. We have a whole new suite of observations. Steve Reiser did an amazing job with the Argo presentation. I was really happy to hear, Luca Santironi talking about the drifters, and we are excited to get drifters into the Banda Sea. And you can see Rama moorings here, and HF radars. But it's really a pivotal time, and we're excited to be working with BMKG. Next, please. And of course, ocean observations, they ground truth the models. So the more data, the more accurate ocean data you can put into a model for initial conditions, boundary conditions, the more accurate your ocean condition, your ocean forecast and climate forecast and weather forecast can be. And that's what we really want to work with BMKG. Next, please. And of course, this is the Indian Ocean Observing System. I would like everybody just to be aware of this because we've been focusing on Eastern Indian Ocean, but you can see there are lots of observations across the entire basin. Next, please. So this is where it all began. I think this is one of my favorite photos. You can see I'm sitting second from the left, and I had brown hair back in 2006. but it's great. It's great. So you can see other colleagues here, and here we are in Bali. This is our first workshop, and it's just one of my proudest professional moments is starting this partnership with Indonesia. Next, please. And we've come a long way. This is our first major workshop with our colleagues from BMKG. Here we're just outside of Bogor. We're at the BMKG Training Center. I think it was It began with a, yeah, thank you, Nellie. Next, please. And you can see we've had support from the highest levels of the U.S. government. Here we are on our Rama cruise with U.S. Ambassador Cameron Hume in 2009. This is on the deck of the Barunajaya. Next, please. And here's the signing ceremony officially with BMKG. The head of the U.S. National Weather Service is signing this agreement in Washington, D.C. at NOAA headquarters with Dr. Andy Sakya, former Director General of BMKG, as we all know. Next, please. And this is fast forward a few years. This is Andy renewing the agreement with the head of NOAA Research, Craig McLean. Next, please. And I'm not going to go over all these, but these are the terms of the agreement. It's an annual workshop. It's an annual cruise. University of Washington graduate student visitors to NOAA's Climate Prediction Center in international desk near Washington, D.C., capacity development, data exchange. The key here is, and this is one of my proudest points, is this is a mutually beneficial partnership. It's a win-win for NOAA. It's a win-win for BMKG, and we're equal partners. And I think that's what sustained this long term. 15 years is a long bilateral, and we're extremely proud of that. Next, please. And this is the 2017 cruise off of Sumatra. You can see the Rama mooring there, and Mike McFadden, our chief scientist for Rama and for the BMKG-NOAA partnership. Next, please. And this is all of us in Bogor last year. It was a great workshop. We were celebrating the 70th anniversary of diplomatic relationships between the United States and Indonesia. And the embassy thought that was so important that the ambassador came down from Jakarta to Bogor. You can see colleagues here, Padodo, former science advisor Josh, and chief of the science office at the American Embassy, Elizabeth. Next, please. And these are just some of the highlights. And the theme last year was improving seasonal climate prediction for national prosperity. But just a fun workshop in Bogor, and very fruitful also. Next, please. This was the most recent successful cruise. You can see 5 Rama sites deployed and serviced off of Sumatra and the Bay of Bengal. Next, please. Here are many workshops. I won't go over all these. I see one in Jakarta, Bali, Bandung, and there's one more. I'm not sure. Oh, I'm not sure where the other one is. But you can see we've been all over the archipelago as we reach out to the Met stations around Indonesia. Next, please. Here's U.S. Ambassador Robert Blake at the launch of the Ina Prima cruise. Again, the highest level of U.S. support within the country of Indonesia. I see Pa Ridwan, director now of BPPT, and other colleagues here. Next, please. Just another cruise. You can see it's really, really good training opportunity for Indonesia as they aspire to develop their mooring program in the Eastern Indian Ocean. Next, please. Just to wrap up here, next, please. We can go through that. Yeah, next, please. Here we are. Back one, please. A big part of the, this is the NOAA Climate Prediction Center, and every year BMKG colleagues come and visit with Silatau and others at their international training desk. Just a couple more, please. Next, please. And then we had a high-level Indonesian trade mission come through Washington, D.C. just a couple of years ago, and here we are with Craig McLean, the head of NOAA Research. Next, please. We're also happy to contribute to the At America events. This is the director of NOAA's observations Dr. Tom Cuff, and you can see with Bu Ita from the embassy. And this is our 2014 workshop in Jakarta, BMKG headquarters. Next, please. And we're just to wrap up, you know, we've come a long way and we're going to go a long way together. I'm very excited, and these are what we're going to be working on in the next year or so. And we can't wait to see everybody in Lake Toba in 2021. Next, please. Next, please. Just terima kasih. I want to say thank you all very much. It's been a great honor working with BMKG over the years. Terima kasih, Bu Nelly. Thank you.
Thank you, Sid. Okay, next I really want to thank you again, Sid, for this arrangement that finally we can conduct our first virtual workshop. But I think we hit a new record here that we have biggest numbers of speakers and also participants. And I want to thank you again for speakers from US and also from Indonesia side. I think all of you give on for our knowledge or for the latest technology analysis, or even the project report that have been done under the umbrella of a US-Indonesia cooperation. I also really want to thanks for the enthusiastic participants, and I think as like Sydney say, that we are very overwhelming with this workshop. And we are also very sorry for the time zone difference for US colleagues, but I hope you also enjoy every moment of this workshop. And I think Sydney, we need to think to have more virtual workshop in addition for our face-to-face workshop. That's all from me now, and I hope that we can strengthen our cooperation, Indonesia, US, BMKG-NOAA partnership. Thank you. See you again soon in Lake Toba, of course. Sheila, you still mute?
Okay. Thank you. So thank you, Pak Sydney and Bu Nelly, for the wonderful closing remarks. It's unbelievable that we've been through 15 years of collaboration between Indonesia, BMKG, and United States of America under NOAA. So without further ado, thank you for all US colleagues and for the participants, Indonesian participants still with us. Without further ado, we still have last session, sesi pamungkas. So for the US colleagues, you are welcome if you want to attend. So without further ado, I just want to call our chair, Bapak Marjuki, to guide our last session. To Bapak Marjuki, time is yours.
Thank you, announcer Mbak Sheila. Selamat pagi menjelang siang Indonesia, and good night for US participant. But I believe that in US now very nice. So if possible, we are using bahasa or mix with English. So I think this is last session, and also the speaker, both of the speaker from Indonesia. Okay, everybody. Selamat pagi menjelang siang. Ini adalah sesi terakhir. Semoga kita masih diberi kekuatan, kesehatan di tengah COVID, kita masih aktif dalam rangka menjalankan tugas-tugas kita dan sekaligus mengikuti workshop dengan tema Climate Extreme Detection, Prediction, and Mitigation on Changing Climate. Pada sesi ini kita memiliki dua narasumber yang luar biasa. Yang pertama adalah Dr. Anastasia Rita Tisyana Dwi Kusuma Wandari. Mbak Ana, please indicate if you are present for this session.
Halo Pak Marzuki. Ya.
Aduh, great. And, how are you Mbak? Apa kabar?
Baik, sudah lama nggak ketemu Pak.
Baik. Kemudian pembicara kedua kita punya Mas Andika Hermawanto. Mas Andika Hermawanto, please indicate.
Ya, hadir Pak.
Baik. Kalau begitu kita mulai pada pembicara pertama. Beliau adalah Dr. Anastasia Rita Tisyana Dwi Kusuma Wardani, menyelesaikan PhD-nya panjang sekali ya namanya.
Iya.
Menyelesaikan PhD-nya Physical Oceanography di China University tahun 2012. Kemudian pernah terlibat beberapa relevan activity di riset ekspedisi Antartik Ocean 2004-2005. Kemudian research fellow in the First Institute Oceanography di FIO dan Ocean Program Officer for Ocean and Climate in IOC Westpac Bangkok, Thailand. Mbak Ana will deliver a presentation about mainstreaming ocean issues in climate change. Please, Mbak Ana, time is yours. You have 20 minutes. Include the question.
Question and answer.
Question and
Okay.
answer. Alright.
Ya.
Please.
Ya, terima kasih Pak Marzuki. Ini yang share screen-nya saya atau siapa? Atau dari panitia?
Kalau
atau
Mbak
saya
Ana
aja?
bersedia ya, kontrol
Ya.
sendiri.
Oke. Tapi nggak bisa. Oh, bisa. Oke. Oke, selamat pagi Bapak, Ibu, rekan-rekan. Ini semua dari BMKG atau dari ada dari saya nggak gitu paham juga. Selamat pagi Bapak, Ibu, rekan-rekan semua. Nama saya Ana. Nama saya memang panjang tapi nama saya panggil saja saya Ana. Saya sekarang adalah peneliti di Kementerian Kelautan dan Perikanan. Sebetulnya saya sering juga sih ikut terlibat dalam beberapa kegiatan BMKG. Terutama dengan timnya Bu Nelly dulu, terus kemudian juga dengan Pak Marzuki, juga dengan kebetulan Andika ini teman saya satu kampung di Cina. Jadi mungkin kami sama-sama ditaruh di sisi ini mungkin karena sama-sama sempat belajar di sana. Untuk presentasi kali ini, saya tidak akan menyampaikan hasil-hasil riset, tapi saya akan menyampaikan, kebetulan saya lihat ada Pak Dodo juga di sini, partner saya dalam biasanya dalam kegiatan perubahan iklim, kami berapa kali bersama-sama terlibat dalam satu tim khusus untuk research and observation dalam isu perubahan iklim. Nah, kebetulan isu ocean biasanya saya yang ikut berpartisipasi atau ikut terlibat dalam kegiatan tersebut. Nah, kali ini saya ingin menyampaikan kepada rekan-rekan di BMKG bahwa saat ini hingga saat ini isu laut itu belum menjadi topik bahasan atau isu yang dibahas di dalam sidang-sidang terkait dengan perubahan iklim, terutama di organisasi UNFCCC yang di bawah PBB, naungan PBB. Kenapa? Karena hingga saat ini kami atau semua pihak yang terkait dengan isu laut itu belum bisa memberikan informasi sebetulnya laut itu seperti apa sih kondisinya, baik sebagai objek yang terkena dampak dari perubahan iklim maupun sebagai sumber terjadinya perubahan iklim. Itu semua belum ada info-info yang jelas atau yang yang firm, oh ya sekian persen loh kontribusi laut untuk perubahan iklim, terus berapa banyak yang terdampak dan sebagainya. Nah, saya pertama kali akan berangkat dari ini dulu. Mungkin kalau ini teman-teman BMKG pasti sudah tahu lah bahwa sebetulnya laut dengan atmosfer itu saling berinteraksi satu sama lain melalui transfer energi baik dari atmosfer ke laut maupun dari laut ke atmosfer dan seterusnya seperti itu. Nah, terus kemudian bagaimana energi itu tertransformasi di laut itu sebetulnya melalui sirkulasi arus. Tadi sudah banyak lah pasti dari pembicara-pembicara kemarin bagaimana sirkulasi arus ini bisa mendistribusi panas dari lintang rendah ke lintang tinggi dan kemudian juga bagaimana menentukan pola hujan yang kemudian juga berpengaruh terhadap iklim regional. Jadi sebetulnya laut ini kan salah satu sumber yang meregulasi iklim, terutama untuk iklim di Indonesia dan juga bahkan bisa mengontrol bagaimana iklim regional. Nah, kenapa bisa begitu? Gitu? Kalau kita lihat dari beberapa sumber bahwa sebetulnya laut ini menyimpan energi sebesar 93%. Terus kemudian kalau kita bicara mengenai emisi CO2, emisi CO2 ini diserap oleh laut itu sebanyak 27%. Jadi kalau kita punya 100% emisi karbon dioksida, 45% itu diserap oleh atmosfer, terus kemudian 28% diserap oleh biosfer, dan laut itu menyerap 27%. Memang lebih sedikit dibandingkan atmosfer dan biosfer, tetapi laut itu bisa menyimpan karbon dioksida itu 50 kali lebih besar dibandingkan dengan atmosfer. Nah, kemudian ini yang kemudian menjadi perhatian para saintis, para peneliti, kenapa laut itu perlu kita mainstreamingkan gitu untuk perubahan iklim. Nah, tahun lalu IPCC itu sudah mengeluarkan report tentang ocean dan cryosphere. Jadi laporan ini khusus berisi tentang bagaimana laut dan cryosphere ini pengaruh terhadap perubahan iklim. Terus kemudian bagaimana satu hal yang sangat saya perhatikan dari laporan ini adalah di dalam laporan itu IPCC secara gamblang menyampaikan bahwa menggabungkan ilmu pengetahuan dengan pengetahuan lokal dan tradisional itu menjadi kunci penting dalam memberikan bukti-bukti nyata terhadap kejadian perubahan iklim. Jadi IPCC ini juga sudah memperhatikan bahwa ilmu-ilmu yang dimiliki oleh, bukan ilmu secara saintifik, tapi ilmu-ilmu yang atau pengetahuan mengenai iklim, kemudian mengenai laut yang dimiliki oleh masyarakat tradisional itu juga menjadi penting untuk memberikan bukti bahwa memang betul terjadi perubahan iklim. Kan biasanya kalau masyarakat lokal itu dia punya insting atau punya pengetahuan dari apa yang dia dapat dari keseharian gitu. Jadi tidak seperti kita yang belajar tentang teori dan sebagainya. Nah, itu ternyata ini juga menjadi menjadi perhatian para peneliti di IPCC bahwa kita juga perlu menggabungkan ilmu pengetahuan dengan pengetahuan lokal ini. Nah, kemudian di dalam laporan ini memang laut tidak dinyatakan sebagai penyebab terjadinya perubahan iklim, tapi lebih berbicara kepada laut yang dinyatakan sebagai objek yang terdampak oleh akibat adanya perubahan iklim. Tetapi kemudian IPCC juga menggunakan skenario ini untuk melihat threshold seberapa besar sih temperatur ini akan berubah gitu. Yang biasanya dipakai, yang sekarang saat ini dipakai itu adalah bagaimana kita harus menekan suhu sampai di bawah 2 derajat itu berdasarkan dari skenario ini. Tapi kalau kita lihat skenario yang tahun 2081 sampai 2100 itu justru tinggi gitu, 4,3%. Tapi ini masih dalam perdebatan mana yang masih mau dipakai, apakah yang 2 derajat atau yang 4,3. Nanti kita lihat lagi. Nah, kemudian saya juga melihat bahwa IPCC juga menekankan beberapa isu yang memang harus diperhatikan. Jadi kalau kita lihat dari gambar ini mungkin terlalu kecil, tapi saya tidak punya gambar yang lebih baik dari ini. Kita lihat bahwa apa yang terjadi di bumi ini adalah tadi memang suhu udara itu akan semakin meningkat, kemudian suhu muka laut juga semakin meningkat, terus kemudian kejadian-kejadian ekstrim itu juga bertambah, kemudian laut juga menjadi semakin asam, oksigennya semakin tipis, semakin sedikit di laut, terus kemudian juga yang masih sering menjadi didengung-dengungkan sebagai efek dari perubahan iklim adalah adanya peningkatan suhu, peningkatan muka air laut. Nah, yang mau saya sampaikan di sini terutama terkait dengan BMKG, mungkin kita perlu bicara mengenai, perlu memperhatikan juga mengenai hal-hal yang terjadi yang di sebelah kiri, di mana suhu permukaan ini semakin hangat, terus kemudian juga beberapa kejadian ekstrim yang menjadi perhatian IPCC adalah terutama mengenai marine heat wave dan juga ocean heat content. Nah, ini dari laporan tersebut kita bisa melihat sebetulnya perubahan iklim itu memberikan impact apa saja terhadap laut gitu. Nah, mereka membagi-bagi menjadi beberapa region. Saya pikir kalau Indonesia mungkin masuknya kepada Tropical Indian Ocean ya, karena tidak ini. Nah, kita lihat yang paling besar itu perubahan itu impact itu akan terjadi kepada apa? Kalau menurut IPCC impact itu justru besar pada saat kita perlu memperhatikan kenaikan atau laut menjadi semakin asam. Terus kemudian juga adanya impact terhadap koral. Ini juga saya pikir ini penting juga untuk Indonesia karena kita terletak di segitiga karang, di mana jumlah karang di Indonesia itu hampir 80%. Dan saya pikir mungkin BMKG juga bisa memperhatikan isu ini juga gitu. Terus kemudian kalau yang lain-lain itu terhadap impact terhadap sosial ekonomi, terus kemudian interaksi manusia dan sebagainya. Nah, apa yang terjadi kalau laut ini menjadi lebih hangat gitu? Yang pertama ada perubahan pada sirkulasi arus laut. Terus kemudian ada perubahan terhadap stratifikasi. Kalau laut itu kan dia ada kolom airnya, terus kemudian punya stratifikasinya seperti mixed layer, terus kemudian thermocline, dan kemudian juga ada yang deep layer. Itu ada perubahan di situ. Terus kemudian ini yang sering didengungkan, ada terjadinya kenaikan muka air laut, terus kemudian ada impact-nya terhadap marine ecosystem tentunya. Kemudian juga ini juga mungkin nanti yang bisa menjadi perhatian juga bahwa ada impact-nya juga terhadap cryosphere. Dan yang sering juga didengung-dengungkan adalah mengenai emisi. Bagaimana karbon di laut ini nanti bisa meningkatkan emisi dan sebagainya. Oke. Nah, ini tadi saya memperhatikan juga bahwa Pak Scott Glenn yang dari Rutgers juga menyampaikan hal ini bahwa ternyata di laut arus laut itu menjadi semakin lambat, terutama di Atlantik. Ini adalah salah satu impact dari adanya perubahan iklim. Nah, kemudian dengan adanya perubahan sirkulasi arus laut yang menjadi semakin lambat ini tentunya juga akan merubah sistem iklim baik secara global juga maupun secara regional. Saya sendiri belum tahu apakah hal itu terjadi juga di Laut Indonesia. Mungkin ini nanti bisa kita lakukan bersama antara saya sebagai peneliti di bidang kelautan, kemudian juga mungkin dengan rekan-rekan BMKG mungkin bisa juga memulai gitu untuk melakukan penelitian seperti ini. Dan juga mungkin teman-teman dari peneliti kelautan yang lainnya. Terus ini kemudian juga ini saya mau hanya menunjukkan bagaimana proses ocean acidification di dalam laut dikarenakan oleh laut itu menyerap karbon dioksida. Jadi di sini saya mau menyampaikan bahwa kalau kita lihat dari peta dunia, laut Indonesia itu kita tidak bisa diketahui seberapa besar sih gitu keasaman yang terjadi ini. Kita masih sangat kurang data. Jadi saya sangat setuju dengan inisiasi BMKG untuk memulai observasi di laut gitu, karena karena kita juga masih butuh banyak data, terutama data-data yang panjang, data yang bersifat time series, karena selama ini data yang kita punya itu hanya bersifat temporary atau snapshot sedikit-sedikit gitu, tapi kita disuruh bicara mengenai bagaimana pengaruh iklim terhadap laut atau sebaliknya, tapi kita nggak bisa bicara apa-apa karena kita tidak punya data. Mungkin dari sini kita bisa berkolaborasi untuk memulai kegiatan-kegiatan yang terkait dengan ini. Mungkin kita bisa pasang sensor pH atau bagaimana di mana di mooring yang dipasang atau dan sebagainya. Mungkin kita bisa bicarakan lagi lebih lanjut. Terus kemudian ini kalau kita bicara tentang kenaikan muka air laut, di sini diproyeksikan bahwa muka air laut itu akan meningkat dari skenario RCP 2.6 itu akan meningkat sebanyak 0,84 meter, tetapi kalau dari yang overestimate dari RCP 8.5 itu akan meningkat sebanyak, kebalik. Dari RCP 2,6 itu 0,43 meter, kemudian dari RCP 8.5 itu sebesar 0,84 meter, hampir 1 meter. Terus kemudian yang juga sering menjadi isu di forum global ataupun forum regional adalah mengenai ocean deoxygenation ini. Memang saat ini seperti biasa di Indonesia belum kelihatan, belum punya datanya, tapi sudah ada sedikit alarming condition. Kalau kita lihat di gambar yang kanan bawah, itu sekitar Selat Sunda itu sudah ada alert, ada warning bahwa di situ sering terjadi ocean deoxygenation. Jadi mungkin kita juga perlu melakukan penelitian-penelitian terkait ini di daerah situ. Nah, ini adalah salah satu hal yang menjadi perhatian IPCC mengenai marine heat waves. Jadi marine heat waves ini dia berlangsung selama beberapa hari atau bahkan bulanan, dan kemudian juga bisa menjadi semakin luas gitu. Saya lihat di Indonesia kita juga belum punya perhatian terhadap ini. Apakah memang terjadi marine heat waves juga atau tidak di Indonesia? Mengingat kita juga mungkin negara tropis, mungkin juga fluktuasi suhu lautnya tidak sebesar negara-negara di lintang menengah atau lintang tinggi. Tapi tampaknya ini juga perlu menjadi perhatian kita karena ini juga mungkin nanti bisa berakibat terhadap iklim, berpengaruh terhadap iklim yang terjadi di Indonesia maupun terjadi secara regional. Kalau ini dari beberapa sumber sudah mulai terjadi marine heat wave. Nah, nanti mungkin kita juga perlu, ya seperti yang saya sampaikan tadi, kita juga perlu memberikan perhatian kan apakah memang marine heat waves ini terjadi di Indonesia atau tidak. Nah, kalau kita bicara tentang spektrum perubahan iklim dan laut di Indonesia, mungkin yang bisa saya sampaikan adalah seperti ini. Secara fisik maupun secara biogeokimikal mungkin Indonesia akan mengalami hal ini. Jadi akan semakin hangat, terus kemudian juga ada perubahan-perubahan keasaman, terus kemudian tadi deoxygenation dan juga sea level rise. Kemudian juga kejadian-kejadian ekstrim seperti ENSO, kemudian marine heat wave, tropical cyclone, walaupun kita tidak tropical cyclone itu tidak terjadi di Indonesia, tapi kita selalu kena dampaknya. Terus kemudian juga storm surge, dan yang mungkin perlu kita perhatikan juga mengenai MGO. Saya ingat tuh Pak Andri pernah membuat riset tentang pengaruh MGO untuk gelombang. Terus kemudian, nah sebagai akibatnya tentunya akan ada terjadi hilangnya beberapa biodiversity yang dimiliki Indonesia juga dan berpengaruh terhadap penangkapan ikan. Tapi kita juga perlu memperhatikan juga, jangan sampai kita juga terjebak oleh romantisme perubahan iklim yang memang selalu menjadi isu atau topik hangat baik di forum global maupun di regional. Karena kenapa? Karena di Indonesia ini perubahan iklim ataupun faktor lokal seperti antropogenik, misalnya pembuangan limbah atau apa dan sebagainya, itu sering dianggap sebagai hal yang sama. Jadi yang menjadi satu tantangan dari kita adalah bagaimana kita membedakan antara apakah ini benar terjadi perubahan iklim ataupun memang karena antropogenik akibat perbuatan manusia yang terjadi sesaat. Jadi itu mungkin salah satu yang bisa menjadi saya berharap juga mungkin BMKG dan mungkin nanti kami teman-teman dari peneliti-peneliti kelautan bisa menjawab itu. Bagaimana apakah fenomena-fenomena yang terjadi sekarang ini emang betul karena perubahan iklim atau efek manusia di darat.
Mbak Ana?
Mungkin dari ya sudah Pak, pas.
You have 5 minutes. Pas.
Jadi itu saja dari saya Pak, nggak panjang tapi saya coba mau memberikan ide-ide mungkin apa yang bisa kita lakukan bersama untuk negara ini gitu Pak.
Oke,
Itu
baik.
aja Pak Juki, terima kasih.
Siap, terima kasih banyak Mbak Ana. Paparan yang sangat menarik sekali mengenai mekanisme atmosfer dan unsur laut terhadap kontribusi perubahan iklim dan dampaknya terhadap laut itu sendiri sebenarnya tadi ya.
Iya.
Baik, saya masih sesuai kesepakatan ada 5 menit untuk tanya jawab. Ini saya bacakan dulu yang di kolom chat, ada satu pertanyaan untuk Mbak Ana. Apakah CO2 yang diserap oleh laut justru bisa meningkatkan pertumbuhan rumput laut dan terumbu karang? Ini pertanyaan dari Mara Sahran. Silakan Bu Ana.
Meningkatkan. Saya sih belum pernah mendengar ada atau belum juga mengetahui bahwa ada pengaruh peningkatan CO2 di laut yang meningkatkan pertumbuhan. Malah justru mendestruktif ya. Jadi sejauh ini yang saya tahu masih bersifat merugikan, merusak. Jadi seperti pemutihan terumbu karang, bahkan kalau kegiatan perikanan budidaya itu justru mereka sangat memperhatikan ini gitu. Jadi kalau misalnya terjadi peningkatan karbon dioksida di laut yang diserap, terus kemudian nanti mempengaruhi keasaman, terus kemudian juga nanti malah merugikan kegiatan budidaya gitu Pak Marzuki.
Oke, baik. Kemudian ada pertanyaan dari Ahmad Rafli. Recalling Bu Ana statement, ocean deoxidation sudah terjadi di Selat Sunda. Apakah dampaknya sudah terlihat di wilayah tersebut? Terima kasih.
Saya sih ya itu. Jadi itu Pak, masih banyak pertanyaan-pertanyaan yang ini sudah ada warning, tapi apakah memang terjadi dampak atau belum? Saya sendiri sampai sekarang juga belum melihat dampaknya secara langsung ya. Tapi kelihatannya memang mungkin terutama untuk komunitas biota laut, terus kemudian juga untuk perikanan sepertinya sudah mulai ada pengurangan, tapi apakah itu memang itu tadi seperti yang saya bilang, saya sendiri belum bisa menjawab apakah memang itu karena deoxygenation atau karena faktor-faktor lain gitu. Karena itu masih kalau di negara kita ini kan hal-hal seperti itu tuh kadang-kadang sulit dibedakan gitu.
Oke Bu, baik. Nah ini adalah last question for your session. Apakah ada cara untuk mengurangi CO2 yang sudah terserap di laut?
Ini pertanyaan susah ini. Kalau ada cara untuk mengurangi ya ini apa namanya? Ya tentunya kita harus mengurangi CO2 yang terlepas ke udara ya Pak ya.
Yeah.
Gitu. Jadi mengurangi mungkin industri, tapi ya itu agak sulit juga ya karena sampai sekarang juga kan ya karena secara ekonomi juga industri masih harus berjalan gitu.
Harus
kan.
jalan.
Jadi, iya, jadi sebetulnya dilemanya perubahan iklim kan itu.
Betul. Bu Ana masih punya 1 menit. Ini ada satu pertanyaan
ya, ini yang terakhir,
tambahan ya. Apakah yang menjadi indikator jika kecepatan arus itu menjadi salah satu dampak perubahan iklim?
Nah, jadi gini, kalau perubahan iklim itu kan terjadi terus kemudian menyebabkan suhu permukaan laut itu menjadi lebih hangat. Nah, perubahan suhu itu tentunya akan berubah terhadap densitas air laut, ya kan? Jadi densitas air laut ini juga jadi kalau kita bicara tentang arus itu sebetulnya kita tidak hanya bicara tentang angin. Jadi arus permukaan boleh kita bicara bahwa pergerakan arus disebabkan oleh angin. Tapi kalau kita nanti kemudian bicara lebih ke dalam, arus laut itu pergerakannya juga ditentukan oleh besarnya densitas. Nah, kalau suhu lautnya berubah, maka densitasnya juga berubah, ya tentunya mungkin akan menyebabkan terjadinya perubahan sirkulasi arus. Gitu, Pak.
Baik, terima kasih banyak Bu Ana atas presentasi yang luar biasa dalam general lecture ini. Dan mari kita beri applause yang luar biasa untuk Bu Ana.
Terima kasih, Pak.
Baik, terima kasih Bu Ana. Silahkan kalau ingin di-mute. Let's move to the next speaker adalah Mr. Andika Hermawanto. He is a doctoral candidate from Qingdao Ocean University of China, and he will deliver a presentation about the oceanic precondition and evolution of 2019 Indian Ocean Dipole. Oke, Mas Andika, silahkan, waktu Anda 20 menit, dan Anda atur sendiri, silahkan, termasuk question and answer. Silakan Mas Andika.
Baik, terima kasih Pak Marzuki atas waktunya. Ini sebenarnya nggak pas banget ini. Ini waktunya paling buncit, pas makan siang dan materinya saya terlanjur ngasih materi yang teknikal banget gitu. Jadi akhirnya tadi malam sempat saya kutek-kutek biar jadi agak-agak nggak terlalu teknis gitu. Halo?
Ya, silakan.
Oh iya.
We heard.
Baik, saya mulai Pak ya. Saya share dari sini. Oke. Oke, terima kasih Pak Marzuki. Di penghujung sesi workshop kita kali ini, saya kebagian kebagian memberikan sebuah general lecture katanya. Saya merasa nggak pantas untuk mendapatkan kehormatan memberikan general lecture di sini, tapi apa boleh dikatalah akan saya coba profesional untuk menjawab tantangan itu. Ini judulnya precondition. Gambarnya agak itu nggak Pak? Kok di tempat saya kayak rada nggak pas ya? Enggak ya?
Enggak masalah.
Terlihat?
Nggak masalah.
Enggak ya?
Nggak masalah.
Good.
Oke, judulnya Precondition and Evolution of 2019 Extreme IOD. Perkenalkan, nama saya Andika Hermawanto. Saat ini saya bekerja di BMKG, tepatnya di Pusat Layanan Informasi Iklim Terapan. Saya agak cepat aja karena ini waktunya juga sebenarnya sudah molor banget. This is my outline. The first, I will give some brief overview about IOD, kemudian dampaknya pada curah hujan di Indonesia secara singkat, kemudian evolusinya seperti apa, dilihat dari subsurface ocean condition, dan sedikit konklusi. Baik, saya awali dengan sedikit recall pada literatur lama. Sebenarnya penelitian mengenai IOD ini sudah lama dilakukan, jauh sebelum Saji 1999 mempublish jurnalnya di Nature, tapi rupanya mungkin peneliti atau komunitas klimater di dunia pada waktu itu belum terlalu melirik kondisi di Indian Ocean gitu, lebih fokus di Pacific Ocean. Ini saya ambil dari Reverdin 1986. Dia menyebutkan bahwa ada anomali zonal dipole yang dilihat dari perawanan di wilayah Indian Ocean pada November 1961. Di situ ada anomali pengurangan perawanan di wilayah timur dan anomali peningkatan perawanan di wilayah timur. Oh ya, Reverdin ini dia menggunakan data sheet dari data pengamatan kapal yang dikumpulkan dari kapal-kapal yang berlayar. Nah, bersamaan dengan adanya zonal dipole pada perawanan ini, ternyata terdapat juga anomali easterly yang kuat di wilayah Indian Ocean Equator bagian tengah. Nah, padahal sebenarnya secara prevailing wind-nya pada November itu angin bertiup dari arah barat ke timur atau westerly gitu. Nah, Ini sebuah anomali. Di samping itu dia juga melaporkan bahwa bersamaan dengan adanya pengurangan perawanan di wilayah timur Indian Ocean itu, ada pendinginan temperatur di wilayah Indian Ocean sebelah timur. Itu berdasarkan Reverdin 1986. Jadi sebenarnya sudah ada penelitian terkait dengan Indian Ocean, tapi belum begitu dikenal waktu itu. Begitu juga dengan begitu juga dengan ini, ada Hastenrath 1993 yang menunjukkan bahwa dia menunjukkan ada korelasi kuat antara zonal dipole dari SST di Indian Ocean dengan curah hujan di Afrika bagian timur. Begitu juga korelasi yang kuat dengan tekanan udara di wilayah Indian Ocean. Kurang lebih seperti itu. Nah, sampai akhirnya kita pada tahun 1997 itu mengalami El Nino ekstrim, sehingga banyak kejadian iklim yang menjadi bahan untuk diteliti. Salah satunya juga Indian Ocean ini yang terjadi misalnya Indian Ocean Dipole yang terjadi di di Indian Ocean. Di sini salah satunya adalah Webster yang mempublish risetnya di jurnal Nature. Dia menunjukkan bahwa memang terjadi anomali SST yang kuat saat bulan September, Oktober, November di tahun 1997, dan itu terlihat jelas dari gambar ini ada dipole gitu, ada merah dan biru di sisi timur dan di sisi barat Indian Ocean. Disertai juga dengan penguatan easterly yang luar biasa kuat di Indian Ocean bagian ekuator Indian Ocean bagian tengah. Saking kuatnya itu terlihat juga dari surface height anomaly atau tinggi permukaan air laut, di mana wilayah Indian Ocean bagian timur itu terjadi penurunan muka laut gitu kalau bisa dibilang ya. Di sebelah barat jadi permukaan lautnya lebih tinggi gitu akibat kuatnya easterly wind yang terjadi saat itu. Kemudian juga bersamaan di dalam paper yang sama itu juga Saji menampilkan menggunakan data yang lebih panjang, nggak cuma 1997 aja, tapi dari tahun sebelum 1960 sampai 1997, dia menunjukkan dan mengilustrasikan dengan jelas bahwa ada kovariabilitas yang kuat antara zonal SST dengan dengan aktivitas konveksi serta angin zonal di wilayah Indian Ocean seperti itu. Dan pada paper tersebut Saji juga memperkenalkan yang kita kenal sampai dengan sekarang, yaitu dipole mode index, yaitu sebuah indeks yang digunakan untuk mengukur kekuatan dari IUD itu sendiri. Nah, mulai dari adanya kejadian El Nino dan IUD ekstrim tahun 1997 itu, para klimatolog di dunia mulai sadar, oh iya ini ada sesuatu fenomena interaksi atmosfer laut yang mirip dengan yang terjadi di Pasifik, tapi ini terjadi di Indian Ocean gitu. Namun dengan mekanisme yang agak berbeda tentunya. Nah, ini penjelasan dari Webster tadi yang lebih detail. Kemudian ini juga saya sepercepat aja. Di samping itu, setelah itu kemudian banyak paper-paper yang mengulas tentang bagaimana mekanisme pembentukan dari Indian Ocean Dipole. Diketahui ternyata bahwa antara IUD yang pure IUD, dalam arti IUD yang tidak dibarengi dengan ENSO, dan IUD yang dibarengi dengan ENSO, itu terdapat perbedaan mekanisme pembentukan yang sangat mendasar. Seperti contoh ini dari sisi sirkulasi atmosfernya dapat dilihat bahwa saat pure IUD yang gambar A ini terlihat bahwa nggak cuma southerly east anomali dan easterly wind anomali yang kuat, tapi ada juga pola antisiklonal yang berpasangan di selatan dan di utara ekuator, serta penjalanan angin yang berjalan dari Indian Ocean bagian tengah ini menyusuri India kemudian ke Laut Arab seperti itu. Sedangkan pada IUD yang berbarengan dengan ENSO itu pasangan antisiklonal tadi itu tidak ada, jadi hanya ada yang di sebelah selatan saja. Itu juga variasi thermocline ternyata berbeda antara apa namanya? Ternyata berbeda antara variasi thermocline yang terjadi di timur Indian Ocean saat pure IOD itu terlebih terlihat pada daerah di lintang 5 hingga 10 derajat lintang selatan, sedangkan saat IOD yang dibarengi dengan ENSO itu lebih terlihat pada wilayah di sekitar 10 hingga 15 derajat lintang selatan. Kurang lebih seperti itu. Jadi memang ada perbedaan antara mekanisme pembentukan IOD saat pure IOD dan IOD yang dibarengi dengan ENSO. Ini saji menunjukkan bahwa ternyata IOD nggak hanya berdampak pada wilayah yang berada di sekitar cekungan Indian Ocean aja, namun ternyata IOD juga berdampak secara global gitu. Jadi kalau dilihat di sini dia menunjukkan bahwa nggak hanya di maritime kontinen, dia melakukan partial correlation antara temperatur permukaan dengan curah hujan. Di sini dilihat bahwa pada wilayah maritime kontinen memang terdapat korelasi yang kuat antara IOD dalam hal ini DMI, Dipole Mood Index, dengan perubahan curah hujan di wilayah maritime kontinen. Begitu juga dengan wilayah di Asia dan bahkan di wilayah Eropa. Jadi memang dampak IOD ternyata nggak hanya di sekitar berdampak di regional sekitar cekungan Indian Ocean aja, namun berdampak secara global melalui mekanisme atmospheric teleconnection. Nah, terkait semakin dikenalnya IOD, kemudian para peneliti juga pengen mengetahui bagaimana sih respon dari IOD ini terhadap isu terjadinya global warming. Bagaimana bentuknya nanti? Ternyata dari hasil, ini saya ambil dari Cheng 2013 menunjukkan bahwa ada istilahnya positive IOD-like warming pattern. Jadi kalau kita bandingkan antara kondisi rata-rata di future dengan kondisi rata-rata saat ini, itu ada perbedaan, di mana perbedaannya adalah wilayah di Indian Ocean bagian timur itu menjadi lebih cenderung lebih dingin, di wilayah baratnya cenderung lebih panas gitu, seperti itu. Makanya disebut, karena mirip dengan pola positif IOD, maka disebut positif IOD-like warming pattern. Nah, di sini kita lihat juga ada easterly yang kuat. Ini menunjukkan adanya adanya interaksi antara pelemahan dari sirkulasi Workel dengan zonal dipole yang ada di SST ini, sehingga menjadikan easterly-nya ini menjadi lebih kuat. Secara kuantitatif kita bisa lihat juga bahwa thermocline di wilayah Eastern Indian Ocean itu lebih dangkal untuk beberapa tahun ke depan. Kemudian di wilayah barat juga lebih dalam beberapa tahun ke depan. Maka kemungkinan untuk terjadi positif IOD itu lebih mudah gitu, lebih sering. Itu dipertegas lagi oleh penelitian hasil dari CHAI 2014 yang menunjukkan bahwa frekuensi ekstrim Indian Ocean atau frekuensi dari ekstrim IOD di masa mendatang itu akan meningkat sebanyak kurang lebih 3 kali lipat dibanding frekuensi kejadian IOD saat ini, seperti itu.
Mas Andika?
Ya.
You have 5 minutes left.
Oops, oke, saya cepat-cepat kalau begitu. Nah, ini dampaknya terhadap Indonesia, ini kurang lebih curah hujannya yang kita alami saat tahun 2019. Indonesia hampir seluruhnya mengalami pengurangan curah hujan. Begitu juga dengan di Australia ada bushfire di sana. Kemudian ini seasonal evolution-nya. Kalau kita lihat di sini, kalau kita fokus ke dipole mood index-nya ini, terlihat bahwa berdasarkan dipole mood index, IOD itu aktif pada bulan Mei di sini. Karena saya katakan aktif bulan Mei karena pada saat itulah nilai dipole mood index-nya melebihi dari standar deviasinya. Namun kalau kita perhatikan yang biru ini masih di atas angka 0, artinya biru ini adalah anomali SSD di wilayah timur Indian Ocean, jadi masih hangat. Jadi walaupun dipole mood-nya sudah positif lebih standar deviasinya, tetapi ternyata Indian Ocean di sebelah timur masih hangat. Jadi kalau kita katakan itu sebagai interaksi atmosfer laut masih belum terjadi. Itu terjadi karena memang kebetulan di wilayah barat Indian Ocean saat itu terjadi panas yang luar biasa, sehingga walaupun di sini nggak sampai negatif, zonal gradiennya sangat kuat. Kemudian itu berlangsung sampai Desember, kurang lebih seperti itu. Ini mekanisme evolusi spasialnya. Kita lihat di sini penguatan southerly dan easterly. Kemudian kita sampai pada subsurface condition-nya. Kita lihat di sini bahwa pada awal ini tadi kalau kita lebih fokus pada kondisi temperatur di sebelah timur Indian Ocean. Nah, ini untuk melihat lebih detail lagi bagaimana kondisi dari anomali temperatur di timur Indian Ocean, saya menggunakan data dari buoy yang terpasang di sini kurang lebih di 5 derajat lintang selatan, 95 derajat bujur timur. Kita lihat di sini bahwa pada awal tahun 2019 memang di permukaan itu terlihat masih hangat, tapi di bawahnya sebenarnya terjadi pendinginan cooling yang saya bilang cukup ekstrim ini. Kemudian kenapa kok bisa di sini terjadi ada anomali positif yang kuat? Kalau kita lihat dari zonal current anomali yang juga dipasang di buoy yang sama ke kedalaman 10 meter, terdapat westward current yang sangat kuat di situ, sehingga dugaan saya ini ada karena ada westward current yang kuat, sehingga ada penumpukan massa air hangat di wilayah Indian Ocean bagian timur, sehingga menjadikan air yang dingin di bawahnya ini tidak bisa naik ke atas seperti itu. Ini ada thermocline di sini yang membatasi lapisan hangat dan lapisan dingin di bawahnya. Ini karena waktunya cukup singkat ya, Pak.
Ya, 1 menit.
Intinya kurang lebih terjadi aktivitas luar biasa di dalam subsurface ini yang bisa kita eksplor sebenarnya. Kemudian ada yang menarik dari 2019 IUD ini, ternyata bahwa kalau berdasarkan dari komposit rata-rata kondisi thermocline di IUD yang umumnya terjadi itu dangkal mulai bulan Agustus, September, Oktober. Namun biasanya ekstrim IUD itu ternyata lebih awal gitu thermocline-nya, pendangkalannya, seperti terlihat pada 2019 tadi. Dan ada yang menarik juga pada paper yang baru keluar dari Wang 2020 menunjukkan bahwa ternyata pendinginan suhu muka laut di timur Indonesia itu nggak melulu diakibatkan oleh ocean dynamic aja, tapi juga dari heat flux yang besar yang terjadi saat IUD terjadi. Karena umumnya pada IUD yang sebelumnya tidak pernah terjadi kondisi seperti itu. Maka ini saya katakan ini sebagai kondisi yang unik dari IUD 2019. Ya,
Sorry to say.
sedikit conclusion Pak, sedikit. Oke. Jadi dalam sesi terakhir ini sedikit saya sampaikan bagaimana perkembangan IUD dan bagaimana prekondisi serta evolusinya, walaupun memang nggak selesai dari karena keterbatasan waktu, serta apa yang poin-poin yang unik saat terjadi ekstrim IUD pada 2009 kemarin. Ya, demikian, terima kasih yang dapat saya sampaikan, Pak.
Terima kasih banyak Mas Andika, paparan yang sangat menarik terkait hubungan prekursor laut dalam hal ini IOD terhadap kondisi iklim terutama di tahun 2019. Bapak Ibu sekalian, saya mengusulkan karena memang waktu kita sangat rigid sekali, bagaimana kalau kita break dulu, kemudian kita menyisakan sesi question and answer, termasuk menyisakan 2 pertanyaan untuk Bu Ana setelah Jumatan.
Bukannya sudah selesai Jumatan, Pak?
Mohon arahan Bu Nelly.
Masih ada ya? Saya pikir udah habis.
Belum, nanti kita lanjutkan. Tapi saya nggak tahu berapa menit.
Baik, ya karena memang kita rigid sekali, menurut saya usul seperti itu kalau diterima, Maka ini kita break dulu, kemudian nanti kita kembali jam berapa?
Jam berapa, Pak? Nggak tahu. Jam 1.
Oke, jam 1.
Ya.
Kita kembali untuk
makan dulu berarti saya ya.
Aduh,
Makan dulu, makan.
Mohon maaf Bu Anak, keep stay in the session.
Saya disandra nih dengan Pak Marzuki nih. Seharusnya bisa tidur siang ini habis ini nih. Jadi nggak jadi nih.
Setelah ini kita unjuk rasa ke panitia ya. Kenapa kita dikasih waktu yang sangat tidak enak ini?
Pak Marzuki. Pak Marzuki.
Iya, Ibu.
Saya Asmi. Saya titip pertanyaan aja ya Pak ya, karena nanti kalau jam 1 saya dimarahin Pak Roma Irama karena akan
silakan Bu Asmi.
Pertanyaan aja ya Pak. Nanti saya bikin di question ya.
Tulis.
Ya, oke.
Silakan ditulis di kolom chat Bu Asmi, gimana kabarnya?
Yap.
Baik, kalau begitu, kalau memang sudah disepakati, maka untuk sesi general lecture ini kita sementara break. Waktu kami kembalikan kepada pembawa acara, announcer. Mbak Sela jangan-jangan udah hilang juga nih.
Hadir.
Silakan Mbak Sela.
Aduh, ya terima kasih kepada narasumber Bu Ana dan juga kepada Pak Andika dan kepada moderator Pak Marzuki yang masih setia. Terpaksa ya jadi skip sholat Jumat. Kami mohon maaf juga kepada para peserta karena kita sedikit out schedule, tapi nggak apa-apa, nanti akan kita lanjutkan lagi pukul 13. Jangan lupa untuk kembali lagi stay tune di link plenary ini, jangan offline atau live meeting dulu karena kita punya Q&A terakhir, sesi pamungkas dan juga penutupan dari Bapak Dr. Dodo Gunawan. Demikian kita break sampai jam 1. Terima kasih.
Terima kasih.
Loh, ini kelas dilanjut ya?
Iya, lanjut.
Wow, break Jumat dulu berarti, Bu.
Iya, jam 1 ya.
Siap.
Stasiun Meteorologi Kelas 2 Silangit Tapanuli Utara merupakan stasiun meteorologi penerbangan dan memiliki tugas serta kewajiban dalam penyampaian diseminasi informasi cuaca di 5 kabupaten kawasan Danau Toba.
Welcome to Silangit Meteorological Station in North Tapanuli. I am head of the Indonesian Agency for Meteorological, Climatology and Geophysics Regional 1 of Medan, North Sumatra. In my right is the head of Silangit Meteorological Station. We present the profile of the Silangit Meteorological Station and Lake Toba area for all the attendants of the 15th Annual Indonesia-NOAA Partnership Workshop. Thank you. Horas, horas, horas.
Stasiun Meteorologi Kelas 2 Silangit Tapanuli Utara merupakan stasiun meteorologi penerbangan dan memiliki tugas serta kewajiban dalam penyampaian diseminasi informasi cuaca di 5 kabupaten kawasan Danau Toba.
Welcome to Silangit Meteorological Station in North Tapanuli. I am head of the Indonesian Agency for Meteorological, Climatology and Geophysics Regional 1 of Medan, North Sumatra. In my right is the head of Silangit Meteorological Station. We present the profile of the Silangit Meteorological Station and Lake Toba area for all the attendants of the 15th Annual Indonesia-NOAA Partnership Workshop. Thank you. Horas, horas, horas.
Stasiun Meteorologi Kelas 2 Silangit Tapanuli Utara merupakan stasiun meteorologi penerbangan dan memiliki tugas serta kewajiban dalam penyampaian diseminasi informasi cuaca di 5 kabupaten kawasan Danau Toba.
Welcome to Silangit Meteorological Station in North Tapanuli. I am head of the Indonesian Agency for Meteorological Climatology and Geophysics Regional 1 of Medan, North Sumatra. In my right is the head of Silangit Meteorological Station. We present the profile of the Silangit Meteorological Station and Lake Toba area for all the attendants of the 15th Annual Indonesia-NOAA Partnership Workshop. Thank you. Horas, horas, horas.
Stasiun Meteorologi Kelas 2 Silangit Tapanuli Utara merupakan stasiun meteorologi penerbangan dan memiliki tugas serta kewajiban dalam penyampaian diseminasi informasi cuaca di 5 kabupaten kawasan Danau Toba.
Welcome to Silangit Meteorological Station in North Tapanuli. I am head of the Indonesian Agency for Meteorological Climatology and Geophysics Regional 1 of Medan, North Sumatra. In my right is the head of Silangit Meteorological Station. We present the profile of the Silangit Meteorological Station and Lake Toba area for all the attendants of the 15th Annual Indonesia-NOAA Partnership Workshop. Thank you. Horas, horas, horas.
Stasiun kelas 2 Silangit Tapanuli Utara merupakan stasiun meteorologi penerbangan dan memiliki tugas serta kewajiban dalam penyampaian diseminasi informasi cuaca di 5 kabupaten kawasan Danau Toba.
Welcome to Silangit Meteorological Station in North Tapanuli. I am head of the Indonesian Agency for Meteorological, Climatology and Geophysics Regional 1 of Medan, North Sumatra. In my right is the head of Silangit Meteorological Station. We present the profile of the Silangit Meteorological Station and Lake Toba area for all the attendants of the 15th Annual Indonesia-NOAA Partnership Workshop. Thank you. Horas, horas, horas.
Stasiun Meteorologi Kelas 2 Silangit Tapanuli Utara merupakan stasiun meteorologi penerbangan dan memiliki tugas serta kewajiban dalam penyampaian diseminasi informasi cuaca di 5 kabupaten kawasan Danau Toba.
Welcome to Silangit Meteorological Station in North Tapanuli. I am head of the Indonesian Agency for Meteorological, Climatology and Geophysics Regional 1 of Medan, North Sumatra. In my right is the head of Silangit Meteorological Station. We present the profile of the Silangit Meteorological Station and Lake Toba area for all the attendants of the 15th Annual Indonesia-NOAA Partnership Workshop. Thank you. Horas, horas, horas.
Where you go, I'll be there. Anytime you whisper my name, you'll see how every single promise I'll keep. 'Cause what kind of guy would I be if I was to leave when you need me most? What are words if you really don't mean them when you say them? And what are words if they're only for good times, then that's all. When it's a lie, yeah, you say them out loud. Those words, they never go away. They live on, even when we're gone. And I know an angel was sent just for me, and I know I'm meant to be where I am, and I'm gonna be standing right beside her tonight, and I'm gonna be by your side. I would never leave when she needs me most. What are words if you really don't mean them when you say them? What are words if they're only for good times, then they're done? When it's a lie, yeah, you say them out loud. Those words, they never go away. They live on, even when we're gone. Anywhere you are, I am near. Anywhere you go, I'll be there. And I'm gonna be here forevermore. Every single promise I'll keep. 'Cause what kind of guy would I be if I was to leave when you need me most? I'm forever keeping my angel close.
There goes my heart. Semua ada di Lazada 99 Big Sale. Tambah ke troli. You are the reason knows my mind racing, and you are the reason that I'm still breathing. I'm hopeless now. I climb every mountain and swim every ocean just to be with you and fix what I've broken. Oh, 'cause I need you to see that you are the reason. There goes my hand shaking, and you are the reason. My heart keeps bleeding. I need you now. If I could turn back the clock, I'd make sure the light to fit the dark. I'd spend every hour of every day keeping you safe. I'd climb every mountain and swim every ocean just to be with you and fix what I've broken. Oh, 'cause I need you to see.
Yeah. Okay.
Halo, selamat siang. Selamat datang kembali kepada para peserta, Bapak, Ibu, rekan-rekan semuanya. Terima kasih untuk tetap kembali di acara kita ini. Seperti yang sudah disampaikan sebelum break, sekarang kita lanjut ke sesi tanya-jawab yang tetap dimoderatori oleh Bapak Marjuki. Semoga kawan-kawan, Bapak, Ibu semuanya sudah lebih fresh, sudah kenyang, sudah menjalankan ibadah sholat Jumat dan sholat zuhur. Kemudian saya kembalikan ke Pak Marjuki untuk dilanjutkan pada Q&A session. Silakan Pak Marjuki.
Terima kasih banyak Mbak Sela selaku announcer. Selamat siang Bapak Ibu sekalian, peserta workshop yang berbahagia. Sesuai dengan janji kita tadi bahwa kita menyisakan waktu tanya jawab ya pada sesi ini. Namun sebelum itu saya ingin memastikan para pembicara sudah join atau sudah ready?
Sudah hadir saya, Pak.
Oke, Bu Ana, terima kasih banyak. Mas Andika gimana? Mas Andika masih mute kelihatannya.
Ya, Pak.
Baik, terima kasih para speaker sudah siap. Kita lanjutkan. Terima kasih banyak tadi apa yang sudah disampaikan Mas Andika dan Mbak Ana cukup luar biasa, dan kita lanjutkan 5 menit, waktu 5 menit untuk lokasi pertanyaan untuk Mas Andika. Jadi ada 2 pertanyaan sementara ini. Yang pertama dari Yosafat Doni Haryanto untuk Mas Andika. Pertanyaannya bahwa penelitian sebelumnya dikatakan kejadian IOD meningkat 3 kali lipat. Apakah kejadian cenderung ke IOD positif atau ke IOD negatif? Apakah itu sebagai bentuk dampak perubahan iklim? Silakan, Pak Andika.
Baik, terima kasih Pak Marjuki dan Pak Yosafat. Jadi Pak, saya baca dulu ya pertanyaannya. Saya kurang mengikuti Pak Marjuki tadi. Dari penelitian sebelumnya, kalau tidak salah 2014 tadi dikatakan kejadian IOD meningkat 3 kali. Oh, maksudnya. Oh ya, ya betul. Maksudnya 2014 tadi yang paper yang 2014. Ya betul. Apakah kejadian cenderung ke IOD positif atau IOD negatif? IOD positif, ya di situ cenderung ke IOD positif. Ya. Jadi kalau seringkali di paper itu kalau dia nggak menyebut positif negatif, menyebut IOD aja gitu, itu cenderung ke IOD positif. Jadi menjawab pertanyaan Pak Yosafat, iya itu maaf itu tadi nggak lengkap saya. Jadi itu positif IOD gitu. Apakah itu sebagai bentuk dampak perubahan iklim? Ya sesuai kalau dari judulnya memang begitu. Dari judulnya dia memang due to greenhouse warming. Jadi kalau apakah ditanya apakah itu sebagai bentuk perubahan iklim? Ya memang begitu berdasarkan dari hasil proyeksi dari model yang digunakan di paper tersebut, kurang lebih begitu. Begitu Pak.
Ya. Terima kasih banyak. Mudah-mudahan jawaban dari Pak Andika bisa memuaskan ya, Mas Yosafat. Nanti kalau memang ini silahkan dikontak beliau melalui email atau SMS atau WA. Nah kemudian ada pertanyaan titipan tadi dari Mbak Asmi sebelum kita break. Untuk Pak Andika, untuk Mas Andika, satu pertanyaannya, projection positif IOD akan semakin sering terjadi in the future. Bagaimana mekanismenya? Wah, banyak ini pertanyaannya ini. Wah, luar biasa ini. ini satu tapi banyak sekali pertanyaannya. Tiga. Gimana? Saya bacakan dulu semua.
Masih ada orangnya loh.
Masih ada ya?
Jawab loh.
Malah. Suruh ngomong sendiri aja. Suruh ngomong sendiri aja.
Gimana? Saya bacakan semua atau dibaca satu-satu baru dijawab?
Baik, saya coba baca aja Pak dari sini Pak ya. Saya juga baca dari di chat roomnya ini. Wah ini pertanyaan yang sebenarnya saya berguru ke Bu Asmi ini, bukan Bu Asmi yang nanya ke saya ini. Jadi baik, saya coba Ibu ya. Projection positif IOD akan semakin sering terjadi in the future. Bagaimana mekanismenya? Bukankah warming climate akan menyebabkan SST meningkat di Eastern Indian Ocean? Oke, sampai sini dulu. Ya, memang warming climate menyebabkan SST akan meningkat. Tapi kalau dibilang meningkat di Eastern Indian Ocean, iya. Cuman kan itu tadi mungkin saya kurang lengkap ya. Jadi antara Indian Ocean di bagian barat dan Indian Ocean yang bagian timur, itu warming rate-nya itu kecepatan menghangatnya itu lebih cepat di barat daripada di timur. Jadi maka dari itu jadi memang kondisi itu akan menyebabkan terjadinya tadi pelemahan dari si westerly wind tadi menjadi anomaly easterly karena warming rate yang berbeda tadi yang lebih cepat di barat yang dibanding timur, jadi menyebabkan easterly itu mudah terjadi gitu, kurang lebih seperti itu. Nah karena easterly-nya mudah terjadi, seperti kita ketahui easterly wind yang terjadi di Indian Ocean Equator bagian tengah itu merupakan salah satu yang menggerakkan terjadinya si IOD tadi, kurang lebih begitu Bu Asmi. Terus mana tadi? Atau warmer climate akan menyebabkan ITF menjadi melemah karena transfer air hangat dari Pasifik ke Indian Ocean berkurang sehingga SST berkurang di Eastern Indian Ocean. Wah ini saya nggak berani jawab, ini pakar ITF adalah Ibu Asmi, jadi saya skip aja dulu ini ya. Kemudian yang nomor 2, apa penyebab westward surface current di IOD mooring beberapa bulan sebelum IOD? Nah ini saya juga ini yang menjadi pertanyaan saya dan sampai sekarang saya masih mencari Bu Asmi. Yuk kita kalau mau bareng-bareng mencari. Terus saya juga lihat ada signifikan positif temperatur anomali di bulan Mei di kedalaman lebih dari 50 mendahului IOD. Kira-kira apa penyebabnya? Oh iya, memang tadi di awal tahun 2019 setelah ada cooling SST di permukaan di bawah 100 sampai 300 tadi, kemudian bulan Mei itu ada shift menjadi positif gitu. Kemudian habis itu menjadi negatif lagi. Ya, itu kalau saya sih menduga karena itu berkaitan erat dengan adanya penguatan westerly lagi. Jadi kalau saya bisa nampilkan di sini nggak ya? Masih bisa nggak saya nampilkan ya? Ya, ini pokoknya dari sisi angin di Indian Ocean bagian tengah itu yang awalnya tadi easterly kuat, tiba-tiba itu habis itu berganti jadi westerly kuat di wilayah situ. Jadi ada penguatan westerly di situ di Indian Ocean bagian tengah. Ya, dan itu kemudian lemah lagi menjadi easterly lagi sehingga itu menjadi kembali menjadi dingin. Kurang lebih gitu Bu Asmi.
Terima kasih banyak Mas Andika.
Pak,
ya.
Terima kasih untuk Pak Andika untuk jawabannya yang sangat jelas, dan saya senang sekali kalau Pak Andika mau kita kerja bareng-bareng untuk terutama menjawab tadi. Berarti itu pertanyaan bersamanya kita. Jadi ya, kalau Bapak mau bekerja sama, mari kita bekerja bersama-sama dengan menggunakan data-data yang BMKG punya ya.
Baik. Kalau anak muda sekarang bilang, siap.
Ya Pak, saya masih muda Pak, jadi saya boleh.
Oke, baik.
Cocok.
Cocok lah, sudah berarti.
Segera diwujudkan. Kita jadi saksi loh ya.
Mudah-mudahan juga bisa
ada saya di sini.
Oh iya, ada Mbak Ana.
Baik, kita lanjutkan. Kita masih punya 2 pertanyaan untuk Mas Andika. Waktunya masih 2 menit. Kemudian nanti ada waktu tambahan untuk Bu Ana ya. Ini pertanyaan dari Mas Aldi ya. Aldi Ripaldi nih. Ini mestinya nanyanya nanti aja lah.
Kalau friend.
Iya, kalau friend. 2015 adalah Godzilla Nino, tapi dampaknya tidak sesever 97. Pertanyaannya, apakah ada kontribusi IOD atau lebih ke SST anomali positif di Indonesia yang menyebabkan tidak terlalu ekstrimnya penurunan curah hujan saat itu? Gimana Pak Andika?
Ya, sebenarnya ini ada kalau mau Pak Adi lengkap satu papernya yang menjelaskan itu. Kalau mau nanti saya kasih paper yang sekalian, nanti kita belajar bareng mengoprek paper itu. Tapi kurang lebih bahwa menyebutkan bahwa saya juga agak-agak lupa Pak Adi. Tapi itu bukan, kalau yang di paper itu disebutkan bukan karena kontribusi IUD yang lebih ke SST positif, tapi lebih ke memang patternnya si El Nino tadi itu agak berbeda dibanding dengan pattern si El Nino yang biasanya terjadi. Saya agak lupa sih. Nanti saya siap nanti ketemu dengan Pak Adi, kita diskusi itu. Saya bawa papernya sekalian. Maaf kalau kurang lengkap menjawabnya Pak Adi. Intinya ada perbedaan pattern di IUD, di ENSO-nya ada yang berbeda gitu. Saya lupa. Yang jelas bukan karena IUD kalau dari paper itu. Begitu Pak Adi.
Oke, saya pikir pertanyaan dari Pak Andika banyak sekali nih, Bu. Apa mau diakomodir semua atau karena waktu kita juga terbatas?
Cut aja Pak, cut.
Mungkin kalau diizinkan saya ini dulu supaya takutnya saya lupa untuk Mbak Ana. Tadi ada 2 pertanyaan yang mungkin belum terjawab. Ini masih ada waktu sedikit kalau bisa. Dari Pak Feriomex ini, dari Om Feriomex. Jadi ada pertanyaan, selain lautan yang luas, kita juga mempunyai danau yang cukup luas. Contoh Danau Toba. Bagaimana kita mengantisipasi kondisi perairan Danau Toba? Apakah kondisi CO2 di Danau Toba bisa diprediksi? Itu pertanyaannya. Silahkan Mbak Ana.
Ya, sebetulnya tadi sudah saya jawab sih di chat, tapi nggak apa-apa.
Oke.
Gini, jadi ya laut dengan danau kan mekanismenya beda ya Pak ya. Gitu. Terus kemudian apakah bisa diprediksi atau enggak? Saya sih belum pernah bekerja di danau ya, tapi intinya saya mau menyampaikan bahwa sebetulnya apapun itu, observasi itu penting gitu. Jadi saya sendiri nggak pernah bagaimana cara memprediksi itu di danau. Saya sih belum pernah ya, tapi saya pikir kalau kita punya observasi, punya pemantauan tentang parameter-parameter tersebut di danau, mungkin kita bisa melihat periodenya lah ya, mungkin gitu. Periodenya seperti apa gitu. Terus kemudian ya mungkin dari situ kita bisa memprediksi gitu. Tapi kan kalau danau itu sangat lokal ya. Jadi mungkin juga ya harus mengetahui juga faktor-faktor lokal apa yang paling berpengaruh terhadap kondisi di danau itu. Kalau dari saya sih itu, Pak.
Baik. Terima kasih. Mudah-mudahan Pak Ferromek masih bisa mendengar. Kemudian ada pertanyaan yang selanjutnya ini dari Ahmad Rafli ya. Di Teluk Lampung sudah 2 kali terjadi fenomena munculnya alga merah yang menyebabkan kematian ikan pada tahun 2012 dan 2017. Apakah ini bisa disebabkan oleh ocean deoxidation tadi, Bu? Gitu pertanyaannya.
Ya.
Silakan, Bu Ana.
Itu juga tadi sudah saya jawab, tapi ya biar lebih lengkap aja di sini.
Biar lebih lengkap.
Jadi kebetulan yang Teluk Lampung itu dua-duanya saya melakukan penelitian yang di situ ya tahun 2012 dan tahun 2017. Itu bukan karena deoxygenation, tapi karena upwelling yang terjadi di teluk. Jadi ada kenaikan dari dasar lautnya gitu ke atas yang menyebabkan terus kemudian Teluk Lampungnya jadi merah dan kemudian ikan-ikannya mati. Itu merahnya itu kenapa? Karena di Teluk Lampung itu banyak kegiatan budidaya. Terus kemudian pakan ikan untuk budidaya itu yang mengendap ke dasar itu karena terjadinya upwelling itu dia naik ke laut. Nah, pakan ikannya ini yang menyebabkan terus kemudian secara kimia saya agak lupa namanya apa, tapi terus kemudian menyebabkan airnya jadi beracun. Jadi kemudian juga itu jadi kebijakan KKP waktu itu untuk berhati-hati terhadap pemberian makan ikan di kegiatan budidaya di teluk gitu, karena itu dapat menyebabkan terjadinya fenomena itu tadi gitu, karena ternyata di teluk itu juga terjadi semacam upwelling, tadi kita nyebutnya upwelling lah gitu. Jadi itu memang itu, tapi bukan karena kekurangan oksigen sih ya, enggak sih gitu.
Ya, terima kasih banyak Mbak Ana. Bu Nelly, saya mohon arahan, ini masih ada 3 pertanyaan untuk Pak Andika, Mas Andika, dan ada satu lagi untuk Mbak Ana. Apakah masih diizinkan atau karena yang untuk pertanyaan untuk Mas Andika ini kebanyakan dari internal, Bu.
Saya sebagai orang luar didahulukan gitu ya.
Sedangkan satu lagi untuk Mbak Ana ini dari anaknya Bu Nelly, ini dari
Iya, ini dari teman saya nongkrong ini.
Luar biasa ini.
Kita suka nongkrong makan es krim bareng dulu.
Gimana Bu Nelly, saya mohon arahan.
Silakan aja singkat-singkat Pak, karena mungkin yang ditanya itu kita juga pengen tahu sebenarnya.
Oh baik, ya sudah siap. Kalau gitu sekalian yang Bu Ana diselesaikan dulu, nanti kita kembali ke Mas Andika. Dari Dava ini, saat ini ada perhitungan Ocean Health Index yang sedang digalakkan di beberapa negara untuk mengukur tingkat sehatnya laut. Apakah hal tersebut juga dapat diterapkan di Indonesia sebagai indikator warning atau alarm untuk kondisi laut di Indonesia? Silahkan, Mbak Ana.
Tentu saja bisa. Karena memang salah satu tujuan dari Ocean Health Index itu kan adalah untuk indikator untuk mengukur dampak dari fenomena-fenomena alam, salah satunya adalah perubahan iklim. Kalau tidak saya ingat, ya perubahan iklim itu adalah salah satu faktor kenapa kemudian dibuat yang namanya Ocean Health Index ini. Karena Ocean Health Index ini kan juga salah satunya yang diperhatikan itu adalah semacam terumbu karang, terus kemudian nggak hanya polusi ya, ada terumbu karang, terus kemudian ada beberapa lagi habitat-habitat lain atau area-area lain yang memang perlu dipantau kesehatannya gitu. Jadi memang salah satunya ya, itu betul sekali. Dan ini sebetulnya sudah dimulai sih kegiatan Ocean Health Index ini. Dulu KKP pernah juga membuat ini, tapi kayaknya sekarang belum diteruskan lagi karena adanya keterbatasan anggaran. Tapi yang pasti kami waktu itu juga bekerja sama dengan LSM, tapi untuk wilayah-wilayah tertentu, gitu. Jadi tidak semua.
Oke, makasih ya Bu Ana. Mudah-mudahan Dava bisa bisa memahami ya. Nanti kalau memang ini silahkan di WA aja.
Sudah lama juga nggak ketemu.
Iya. Selanjutnya kita kembali ke Mas Andika. Ini ada 3 pertanyaan. Seperti saya bilang, ini dari kolega-kolega internal sendiri, dari Pak Supari. Kalau El Nino biasanya dipicu oleh westerly wind burst yang kuat dan berulang-ulang. Nah, kalau IOD dipicu oleh apa? Karena arah pergerakan SST hanya berlawanan arah. IOD positif hangatnya di bagian barat. Silakan, Mas Andika.
Ya, kurang lebih sama sih kalau sepanjang pengetahuan saya, Mas Pari. Jadi kalau di Pasifik ada westerly wind burst, di di apa namanya di Indian Ocean itu juga itu tadi dia dipicu oleh adanya anomali easterly yang kuat di Indian Ocean bagian ekuator itu tadi, yang di bagian tengah tadi, serta southeasterly di barat Sumatera tadi. Jadi itu kan yang menyebabkan si Wilkie Jet yang menyebabkan Indian Ocean bagian timur menjadi hangat itu menjadi tidak hangat lagi, itu kan gara-garanya si easterly wind tadi itu gitu. Jadi kurang lebih seperti itu. Jadi hampir sama kurang lebih kalau mungkin kalau dianalogikan sebagai westerly wind burst di Pasifik, ini ada easterly di Indian Ocean gitu, dan southeasterly di barat Sumatera, kurang lebih seperti itu.
Baik, terima kasih banyak jawabannya. Kemudian pertanyaan selanjutnya adalah dari Khalid R. Pratama. Apakah ada kaitan kuat antara IOD dengan penguatan Somalia Jet dalam kasus peningkatan frekuensi SST di barat maritim kontinen?
Berat ini pertanyaannya. Saya kayaknya bukan ahlinya untuk yang ini Pak Khalid. Jadi mohon maaf saya belum bisa menjawab ini. Nanti bisa jadi pemicu saya buat mencari informasi terkait itu juga nantinya. Terima kasih sebelumnya. Mohon maaf saya belum bisa menjawab.
Oke. Kemudian ini dari Feriomek ya, Om Feriomek untuk Pak Andika. Seberapa besar pengaruh IOD terhadap kondisi cuaca di wilayah Sumatera Utara?
Dia mewakili Danau Toba soalnya.
Iya, seingat saya kalau semoga saya tidak salah, ini koreksi kalau salah ya Pak Feriomek. Feriomek ini teman saya Pak, satu angkatan ini Pak. Jadi jadi untuk Sumatera itu yang paling berdampak dari IOD itu di Sumatera bagian selatan gitu, sebagian di Sumatera yang bagian tengah, dan Sumatera yang di bagian utara itu ada sedikit beda dengan yang lain gitu. Jadi kalau sebagaimana dengan terhadap kondisi sumut, apa pengaruhnya besar, seberapa pengaruhnya besar. Yang jelas memang ada perbedaan antara Sumatera yang di bagian selatan dengan Sumatera Utara terkait pengaruh IOD terhadap wilayah di Sumatera. Mungkin itu jawaban saya, Pak Mek.
Ya, makasih. Ini ada satu lagi nih dari Pak Aldi, Adi Ripaldi ini. 2019 adalah IOD tertinggi sejak 30 sampai 50 tahun berbarengan dengan pelemahan El Nino. Pertanyaan yang sama, what is the most robust phenomena, IOD or El Nino? Yang paling mempengaruhi turunnya curah hujan dan mundurnya musim pada tahun 2019.
Jawaban tepatnya kurang tahu, tapi jawaban spekulatifnya saya menjawab ini sebagai IOD gitu, dibanding dengan El Nino gitu. Sekali lagi ini jawaban spekulatif ya, bukan jawaban tepatnya ya. Dan juga karena nggak bisa ngomong asal. Ini tadi ngomong berdasarkan feeling saya aja, nggak berdasarkan data. Jadi kesannya kalau yang di 2019 itu kan justru El Nino-nya kan cenderung lemah dan netral, nggak salah ya. Sedangkan IOD-nya kan ekstrim. Nah, sedangkan main kontributor terhadap pengurangan curah hujan itu kan IOD positif dan El Nino gitu. Jadi kalau El Nino-nya lemah netral ya berarti satunya yang paling berpengaruh. Mungkin itu jawabannya. Jawaban spekulatif Pak Adi, mohon maaf.
Oke. Kita masih punya 2 pertanyaan. Maybe this last one lah mungkin ya. Ini dari Pak Roland Bineri ya. Ada 2 pertanyaan. Yang pertama, bagaimana pola normal El Nino yang biasa terjadi? Apakah akhir-akhir El Nino La Nina yang terjadi sudah mulai berubah polanya? Silakan.
Ini pola normal ini maksudnya terhadap curah hujan gitu maksudnya kali ya?
Curah hujan ya.
El Nino La Nina. Mana ya jawabannya ya? Bagaimana pattern normal El Nino yang terjadi? Ya, ini saya kurang lebih jawabannya formatif aja. Yang biasanya terjadi itu yang paling terdampak kuat itu untuk Indonesia dari El Nino itu wilayah Indonesia Timur dan wilayah Indonesia bagian tengah gitu. Jadi wilayah bagian barat relatif lebih banyak dipengaruhi oleh si IOD daripada El Nino, kurang lebih begitu. Kalau ditanya bagaimana pola normal El Nino terhadap Indonesia, jadi mungkin normalnya hanya wilayah timur dan wilayah tengah Indonesia yang bukan hanya yang maksudnya yang lebih relatif lebih terdampak gitu terhadap adanya El Nino di wilayah Indonesia. Mungkin seperti itu, Pak.
Ya. Bu Nelly ini dengan antusiasme pertanyaan terutama dari internal ini sebenarnya menunjukkan
Kayaknya
kita
perlu di-stop, Pak.
jarang diskusi sebenarnya.
Itu bener, jarang diskusi.
Jadi
bener.
mohon Bu, nanti setelah
Atau
ini
ada
mungkin
bintang
sering ada
Andika.
event Bu.
Masih
Jangan lupa saya diajak Bu Nelly.
Mas
Iya,
Andika
bener.
ini jarang keluar, Pak.
Oh, makanya saya paksa keluar hari ini.
Iya. Kuper
Bukan,
ya.
Yuki.
Baik. Mulai
Gara-gara
besok
nggak
aja.
kemana-mana,
Kita ini
Pak.
PSBB ya sih.
Padahal satu-satunya yang concern mengkaji masalah IOD itu Pak Andika.
Gitu ya.
Baik, maafkan saya.
Jagonya EO di BMKG.
Pak Yuki.
yang dipercepat.
Pak Yuki.
Siapa?
Ini karena nggak banyak kemana-mana, jadi banyak.
Baik, ini supaya adil ada pertanyaan.
Nggak kemana-mana.
Iya, ada pertanyaan dari Pak Sis, saya harus sampaikan.
Ini yang Bu Ana belum loh itu. Pertanyaan buat Bu Ana.
Ya Bu, nanti setelah ini nih, mudah-mudahan itu terakhir terus Bu Ana kita jadi pamungkas.
Oh iya.
Aduh, nasib.
Jadi Pak Andika, ini dari Pak Siswanto. Pak Siswanto, kalau di Pasifik ada variabilitas antar dekadal dari ENSO yaitu PDO. Apakah di Samudra India ada variabilitas serupa? Mengingat IOD dalam beberapa dekade terakhir lebih dominan IOD positif.
Nih, kembali ini jawaban spekulatif Pak Siswanto. Jadi kalau menurut saya dalam para ilmuwan klimat ini kan dalam memandang IOD ini ada dua mazhab ini kan. Ada yang memandang itu IOD itu sebagai fenomena interaksi atmosfer laut yang berdiri sendiri dan ada yang itu sebenarnya respon pasif dari El Nino gitu. Jadi kalau saya mencoba mengikuti mazhab bahwa IOD ini merupakan bagian atau respon pasif dari El Nino, sedangkan ENSO maksud saya, sedangkan tadi Pak Sis bilang di ENSO itu ada PDO, nah apakah di Indian Ocean juga ada serupa yang PDO? Nah maka dengan analogi itu maka saya mengatakan iya ada Pak, kalau memang saya mengikuti mazhab dari bahwa IOD ini bagian respon pasif dari ENSO, bukan sebagai fenomena yang berdiri sendiri. Mungkin begitu Pak Sis.
Oke, makasih. Saya pikir
makasih.
Untuk Mas Andika selesai ya, tapi ini ada pertanyaan satu nih Bu Ana, jangan sampai nanti nggak bisa tidur yang nanya. Apakah untuk Bu Ana ya, apakah ada marine heat wave yang terjadi di sekitar wilayah perairan Indonesia? Seberapa besar pengaruh marine heat wave di Pasifik yang mengakibatkan ENSO? Silakan Bu Ana.
Iya, Pak Roland, terima kasih pertanyaannya. Justru itu yang tadi jadi pertanyaan saya sebetulnya kan tadi di presentasi saya begitu. Ini sebetulnya di Indonesia ada nggak sih marine heat wave ini gitu? Apakah kita perlu juga memberi perhatian terhadap marine heat wave ini gitu? Karena kan ya itu tadi fluktuasi suhu permukaan laut di Indonesia kan tidak terlalu range-nya tidak terlalu besar seperti kalau kita di lintang menengah atau lintang tinggi gitu kan, ada musim dingin, musim panas gitu. Tapi justru itu Pak, sebetulnya ini juga pertanyaan saya, apakah betul di Indonesia juga, apakah di Indonesia juga ada atau tidak. Jadi karena saya juga belum tahu, berarti pertanyaan kedua Bapak saya juga tidak bisa jawab. Karena seberapa besar pengaruh marine heat wave, saya juga lagi mempelajari itu Pak. Jadi mungkin jawabannya nanti setelah saya pelajari Pak.
Baik, terima kasih Bu Ana. Bapak Ibu sekalian, saya pikir itu menjadi pertanyaan atau dan jawaban pamungkas ya pada sesi general lecture siang hari ini. Luar biasa sekali para pembicara kita. Maka untuk sebagai closing pada sesi ini, mari kita beri applause yang luar biasa untuk pembicara kita. Demikian, sekali lagi terima kasih banyak untuk Bu Ana dan untuk Mas Andika. Sehat selalu dan waktu
Sama-sama
kami
Pak,
kembalikan.
sehat selalu untuk kita semua.
Siap, dan waktu kami kembalikan kepada pembawa acara. Mbak Sela, silakan Mbak Sela.
Ya, sudah bisa kedengaran ya. Oke, terima kasih kepada Pak Marjuki dan juga kepada para panelis Ibu Ana dari KHP dan Pak Andika dari BMKG. Kita sudah punya Pak Dodo di sini. Mungkin langsung bisa ditutup secara resmi oleh Bapak Dr. Dodo Gunawan. Kepada Pak Dodo, langsung saja Pak, kami persilahkan.
Baik, terima kasih Mbak Sela. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang, salam sejahtera untuk kita semua. Saya bahasa Indonesia aja ya, karena teman-teman Amerika sudah pada sudah nggak ada ya. Iya, yang terhormat Ibu Kepala Pusat Penelitian dan Pengembangan BMKG, yang terhormat Ibu Ana narasumber, kemudian juga narasumber yang lain, dan seluruh peserta workshop ini. Pertama-tama tentu kita panjatkan puji syukur kepada Allah Subhanahu wa Ta'ala, yang mana telah masih memberikan kita kesempatan mengikuti acara workshop tahunan dari BMKG yang bekerjasama dengan NOAA, yang kita lakukan sejak hari Rabu ya hingga hari ini Jumat 11 September. Kita telah mengikuti rangkaian, ada general lecture, ada paparan dari para peneliti Indonesia, para saintis Indonesia, ada juga hands-on training sebenarnya. Jadi workshop ini merupakan rangkaian dari kegiatan kerjasama, salah satu dari bentuk kerjasama BMKG-NOAA. Bentuk kerjasama yang lainnya itu ada penelitian kelautan ya, dengan aktivitas atau kegiatan pelayaran di Samudra Hindia terkait dengan pemeliharaan buoy, alat observasi di laut, dan juga ada training di NOAA untuk staf BMKG ya, International NOAA Desk namanya. Dan juga ada pengiriman mahasiswa dalam kaitan kerjasama ini ke universitas di Amerika. Jadi kita biasanya melaksanakan kegiatan ini secara workshop physical meeting ya. Sesuai dengan judul ini kegiatan yang ke-15 kalinya, sehingga beberapa waktu yang lalu itu kita secara rutin para expert dari NOAA dan Amerika ini, yang lainnya ada yang dari perguruan tingginya juga, itu hadir untuk melakukan workshop ini. Namun karena situasi saat ini pandemi COVID-19, ya kita tidak bisa melaksanakan secara fisikal dan kita laksanakan secara virtual. Namun ini barangkali kita terima kasih juga ke COVID ini, dengan kondisi seperti ini, ya kita bisa mengundang secara lebih banyak peserta ya melalui virtual ini, melalui online ini, melalui fasilitas meeting seperti ini, menggunakan Zoom, itu dapat mengundang lebih banyak peserta yang berminat keahlian di bidang iklim dan kelautan. Jadi ini ada dua, kami membagi dua, sehingga di dalam pelaksanaan kelasnya pun atau pelaksanaan ini secara paralel ya. Sebenarnya semuanya ini sangat berkaitan dan kami sangat sayang untuk melakukan secara paralel ini. Namun tentu juga kita tidak bisa kalau diserieskan secara seluruhnya panel gitu, karena mengingat secara virtual ini kita berinteraksinya dengan teman-teman ataupun narsum ataupun mitra dari Amerika yang waktunya sangat perbedaannya sangat jauh, sangat ini ya, sangat besar gitu. Saat ini mereka sudah tengah malam atau menuju pagi gitu. Sementara kita bisa. Ini pun kalau masih ada mereka ya, saya mengucapkan terima kasih ke para narasumber yang dari Amerika ini dengan segala keterbatasan ataupun perbedaan waktu ya, mereka dapat meluangkan untuk mengisi acara ini sehingga kita dapat paling tidak menimba ilmu ya dari mereka, dapat mendengarkan langsung dari ahli-ahli yang berkecimpung di bidangnya ya. Banyak sekali di sana, ada yang ke lautan ataupun atmosferik gitu. Sehingga kita bisa menambah wawasan. Juga selain di Zoom ini, kita ikut ini juga di streaming juga di YouTube, sehingga kami mengharapkan mungkin apa yang sudah diikuti ini kiranya dapat dimanfaatkan oleh rekan-rekan semuanya, dan saya melihat ini ternyata banyak sekali para milenial ya. Jadi pesertanya ini baik dari BMKG secara keseluruhan, dari UPT dan juga dari luar, mungkin saya lihat banyak sekali yang generasi milenial, sehingga saya kira ini mudah-mudahan dapat menambah wawasan keilmuan, dan tentu saja karena kita bekerja secara langsung untuk operasional sehari-hari ya, mudah-mudahan ini dapat menjadi dukungan pekerjaan kita, keseharian kita, pekerjaan kita, analisis iklim, cuaca, dan masalah di kelautan ya. Jadi silakan ini misalnya dari rekan-rekan ini ada yang masih penasaran, ada yang belum paham sepenuhnya, bisa mengontak langsung ke para narasumber tadi yang mungkin ada kontaknya, dan juga tentu kami di BMKG ada dari Pusat Informasi Perubahan Iklim, ada dari Puslitbang, ada dari Pusat Meteorologi Maritim, ada dari Pusat Layanan Informasi Iklim Terapan di Kedeputian Klimatologi ya. Silakan kalau ada hal-hal yang ingin ditanyakan baik dari rekan-rekan BMKG nasional maupun juga dari rekan-rekan yang ada di instansi kementerian ataupun universitas. Jadi itu mudah-mudahan ini workshop ini masih bisa berlanjut, bahkan barangkali kalau sudah dalam kondisi normal kita juga akan melaksanakan juga secara normal seperti itu ya, ada physical meeting. Mungkin karena bagaimanapun ada plus minusnya lah antara pertemuan seperti ini virtual dengan keterbatasan perbedaan waktu ya. Mungkin kalau secara fisikal barangkali bahkan bisa berdiskusi secara lebih intens seperti itu, sehingga biasanya antara Agustus atau September kita melakukan workshop ini, dan juga tentunya kegiatan-kegiatan yang lain dalam kerangka kerjasama BMKG-NOAA ini ya. Kemarin kami juga sudah membicarakan terkait kegiatan-kegiatan tahun depan, termasuk rencana cruise dengan layar ke Samudra Hindia. Jadi itu sekali lagi kami mengucapkan terima kasih kepada narasumber ya, kemudian juga tentu kepada panitia ya. Ini walaupun secara virtual, secara online meetingnya, tapi persiapannya tetap saja gitu ya, sama juga tidak kalah sibuknya gitu panitia. Untuk itu kami mengucapkan terima kasih atas keberhasilan dan berlangsungnya acara ini. Walaupun tentu sifatnya juga teknologi seperti ini, di sana sini masih ada kekurangan dari koneksi, mungkin secara teknikal ada hal yang kurang berkenan. Untuk itu mohon atas nama kami panitia mohon maaf apabila ada hal yang kurang berkenan, kurang memuaskan selama jalannya workshop ini. Saya kira demikian yang dapat saya sampaikan sebagai penutup acara ini. Sekali lagi terima kasih atas perhatian seluruh peserta dan juga seluruh yang hadir pada acara workshop ini. Dengan ucapan alhamdulillahirabbil alamin, the 15th annual Indonesia US BMKG-NOAA Partnership Workshop dengan tema Climate Extreme Detection, Prediction, and Mitigation on Changing Climate, saya nyatakan selesai dan ditutup. Terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Terima kasih Pak Dodo dan teman-teman.
Terima kasih Mbak Ana.
Ya, terima kasih Pak Dodo Gunawan sekaligus menutup rangkaian acara workshop kita selama 3 hari terakhir ini. Sekali lagi atas nama panitia, saya selaku MC pada hari ketiga ini mengucapkan banyak sekali terima kasih kepada para rekan panitia, kepada para peserta, dan yang paling penting juga kepada seluruh narasumber, moderator, dan panelis. Terima kasih juga kepada dukungannya dan arahannya kepada Ibu Kapus, Ibu Nelly. Informasi terakhir ditujukan kepada para peserta, jangan lupa untuk mengisi kuesioner dan juga mengisi daftar hadir apabila bagi yang belum mengisi daftar hadir. Link sertifikat akan dikirimkan kepada email masing-masing peserta. Demikian dari saya, kurang lebihnya atas nama panitia kami mohon maaf sekali apabila ada keterbatasan ataupun ada yang kurang berkenan terutama di permasalahan teknis.